All right, so I think it's getting about 8:05, so we'll get started just because it's going to be a full day class, so we want to make sure that we get through all the material today and also leave plenty of time for questions. That's something that, just throughout the day, if you have any questions, just feel free to raise your hand or just shout it out, and we can talk about whatever you want to. So my name is Herman Holm. I am part of the Flares business unit for Sage Environmental. I've been solely dealing with flares for getting close to 3 years now. We've been involved in a lot of the early and ongoing flare consent decrees, heavily involved in NSPSJA implementation. We took when Sage started doing this flare work, we took a slightly different approach than in some other firms, where we not only wanted to know the rule, we also wanted to know the technologies around the instrumentation and monitoring. So we made sure that we talked to the people who made the devices and got to know about those technologies. So we hope that this will be an interesting course. Always want to start off with the safety talk. Exits, just out these doors, and there were emergency exits either to the left or to the right. There is, and if I know yesterday we had some issues with the fire alarm. Hopefully that's not going to occur today, but our general policy is the alarms go off. We don't wait to see if there's a fire. We just leave the building and come back. So we'll do that unless we're instructed otherwise. The restrooms are down to the right, and I think coffee's in the exhibition hall. So, for today, it's just to talk about flares and, hopefully have a good time doing it. I know there's a lot of different issues going around, and flaring is really one of these topics that is kind of an ever-evolving subject right now. We have new rules coming out all the time. We have new studies coming out. We have actually, as of last Friday, we had a new technology not a new technology, but an existing technology looking for to be able to not follow some of the rules. So and this is all exciting stuff. So hopefully we can provide the information that'll help you guys out. As I said, ask questions. And sometimes the best classes we have are the ones where people ask the most questions. We've seen a lot of flares, but sometimes you've had an experience at your site where you've seen something we've never seen before, because that's one of the great things about flares, at least keeps me interested, is that every single flare system is different. We've seen over 200 of these things, and they are never the same. There's always some difference in setup, what you're doing with them, how you're operating them, and that's just where the fun comes in, at least for me. But as I said, my name is Herman Holm. We're going to have two other presenters today. We have Rishabh Jaishankar. He's also with Sage Environmental out of our Atlanta office. It just so happens that a lot of the flare people for Sage are in Atlanta. And then we got Tom Goddard. He's in our Houston office. He's going to be doing the section when we talk about the upstream sector and NSPS Quad-O. So hopefully we can all have fun today. One of the things we like to do, just to make sure everybody's interacting, is we like to just go around the room, just say your name, who you're with, and anything else you'd like to share with the room, just so we...
Mitch Morris, Williams, interested in the Quad-O discussion.
Okay, great.
Sophia Adika, Mental Resources. Turn it up on all.
Ashley Budrick, Marathon Petroleum. I'm a co-op there for this term, so just get more knowledge about on there.
Great.
Spend most of your time in refining the use of the string. my background is petrochemical refining, plastics. So my short story is I actually have been calling around the flare guys, the true flare guys like Herman, and I end up being their chauffeur when they come to the Houston area. And I've learned a lot. I really raised my hand to be here, and it's been great. And I've learned a lot over the last year and a half. So it's great to be here.
My name is Edward Lee. I'm from Northfield Chemicals. I'm based in Texas. Happy to learn about flare. We have one flare going to compile in Marshall. I'm here.
Hey, I'm Daniel Denslow. I'm with Quest Consultants with Norman, and I just think flares are pretty interesting. I'd like to learn more.
Excellent.
Blake Morrell, ESF reports. We have 3 different types of flares in my block, so I work with them quite often. I'd like to learn more.
John Berry with Unpaid Group, and also trying to learn a little bit more about flares. Work on more in some other areas of our company.
Mr. Ali, I'm from environmental intellect. Flares are new things to me, so I'm here to learn.
Okay, great.
Todd's in the state of Michigan, DEQ, and I work out of the Detroit office, and I'm just here to learn.
Pat Gillis with ESC. We're a gas vendor, so we monitor and do reporting off of these, and I just want to learn more about the whole process.
Mike Bankley with Westlake Chemicals, Calvert City, Kentucky. Flare.
Daryl Page looking for Bill Bell with Advanced Analytical, who do gas photographs and sample systems.
I'm Rashad Deschamps, and I'll be helping Herman and Tom present today. I've been with Sage for a couple of years now and pretty much focused only on flares, so looking forward to meeting all of you and interacting with you today.
Yeah, and one thing that we also wanted to say, like with your questions, if you feel like you want to talk about your neighbor's flare, we're more than happy to answer those questions. I know sometimes people don't always want to have the focus on them, but okay, so this is just a bunch of people that are part of the flare team. Troy Boley, who teaches this class a lot with me, he's actually up in the flare experts room. That was a 3-day course that we offer. We did the first day yesterday, and it was when we go through the regulations in about a portion of the day, we spent all day yesterday talking about nothing but regulations and flaring. So it's we're going to touch on a lot of things here, and it just keeps going and going as what you can learn. We got myself, Tom, Derek Stuck is also one of our key project managers for our flare projects, and he's upstairs with Troy. So if you guys run into these guys in the exhibit hall or around, feel free to talk to them. They'd love to meet you. Okay, so when we structured this class, we knew that we're going to have people that have different knowledge bases. But we wanted to start out the class with just getting everybody kind of on the same page. So I mean, we're going to talk about everything from, what is a flare, a knockout drum, a water seal. We're going to go all through those kind of component type things. We're going to talk about the different gases, where you inject them, why you inject them, how they affect the system. We're going to talk about some rules. We're going to talk about them enough to show you that these things are complex, and we'll go into a good level of detail. But I mean, there's just a ton of stuff there. We'll get into one of the 2 biggest changes in flare regulation, at least on the downstream side, was NSPS-JA, which was an SPS that focused on the refinery sector, which had flaring requirements and flaring limitations. And now they proposed changes to the Refinery Act. The comment period just ended in this last fall, and that is going to add a whole bunch of new monitoring requirements and control for refinery flares. One of the things, I know we have some people here from the chemical side. From what we can tell, the things that they're proposing in MAC-CC follows very closely what has been in the flare consent decrees, and we see that this is the path that is going to be going to the chemical side. So it is, many of the concepts are going to be very similar. There are some there is a lot of differences between the refining side and the chemical side, just by the nature of different processes, and you guys handle things a little differently, but many of the key concepts do carry over. We're going to talk about oversteaming and over-assisting a lot today. There's right, if you don't know, there's the EPA enforcement right now is focused on flares. So I mean, there's been a lot of activity around flares, and the fact that if you're over-assisting your flare, you're not getting proper combustion. So that we're going to talk about that in a lot of detail today. We'll talk about some of the recent EPA enforcement actions. You know, we will just focus on the flaring side of those. We're not going to, because these consent decrees cover more than just flaring, but we're just going to talk about flaring. We're going to talk about the technologies behind the monitoring. This is a complex issue, and it's given, you know, the rule comes out and it says, oh, put in a flow meter. Well, we're finding out that the flow meter is that's not a simple thing. We are, you know, it's a highly complex system, and the technology is great, but it also has issues that are needing to be overcome, and there is no great fix for it yet. And then we're going to also get into, once you have that monitoring in place, how are you going to control your flare to meet all these requirements and show that you're operating your flare well. So I mean, we're kind of going to run the gambit. So again, stop me at any time. I tend to talk fast when I get excited. So you know, if I get going too fast, just slow me down. I won't take offense. This is kind of a loose schedule. I think we did this before. Lunch is only going to be an hour, so that will be from 12 to 1. Generally, when we do this class around the country, about 4 to 6 times a year, and you know, it's, you know, different size groups, but we have these hard breaks. That's when they're going to have coffee and snacks and stuff like that. But we'll break anytime we need to. We're not so structured that we can't. You know, if everybody's got through a section, we're all saying, you know, well, we need to take a 5-minute bathroom break. We'll do that. We're not going to be stuck to these breaks, but we will try to keep things moving. So you can kind of just see here all the different topics we're going to run through. Okay, so one of the big questions is, what is a flare? That's that, you know, you think everybody's kind of used to this picture. You got the nice big stack, got a ball of fire on top of it. Everybody's pretty sure about that. That's a flare. And then people started saying, well, I got this thing right here. It combusts waste gases. You know, I think they even called it in my permit. It's called an enclosed flare. But is it a flare? The big defining line that, especially when NSPSJ came out, was the flare is defined by its combustion in uncontrolled amounts of air. So I mean, that's like when the flame is outside of the tip, you know, it's in the ambient oxygen. So I mean, it's not, you can't control that air. So that is kind of that key defining thing. So when you have these, we like to call these more likely when they have like this louver system and blowers where they're able to tweak that air and they're trying to maintain a certain temperature inside of the combustion area. Those then are not flares. Those are what we like to call those vapor combustors. And it is just that. And just because you don't want to have all the rules on this, and they don't function in the same manner, you wouldn't operate those. You're never going to have a flare and have a permit requirement to say you must maintain some degrees in the combustion zone, because there's no way for you to do that. So I mean, but when you have an enclosed combustor, you know, you're going to have temperature probes. You're going to be either adding fuel or controlling air to maintain that temperature. So I mean, it's a different technology and a different system.
Open air, high temperature condensation. Where does that come to that classification?
The open air concept is definitely has come out through EPA's, you know, people have questioned the whole what is a flare, because there was a lot of discussion about air assisted flares, and you know, you're providing air to the combustion zone, and EPA came out and firmly said that no, an air assisted flare is a flare, and that is also due to its ball of fire up above the tip. So that the EPA came out and was very distinctive about how that happened. And then it's just, you know, it's here using general terms. I mean, you're having oxidation, you're having combustion, but even out of the combustion zone, there's still going to be breakdown of products. And it's just, mostly it's you know, the combustible vapors that's why we have them, is a safe way to get rid of those vapors. So I mean, this definition I don't think came from anywhere. I think it's just something we put together.
So the combustion tip flare is at the tip of the flare.
Yes. Yes. No. There are enclosed flares. I don't want to mislead anybody. There are flares, ground level flares, which are enclosed, but they have no means of controlling the air that's getting to them. There's no louvers or anything like that. So you'll have a lot of times they'll put ground flares and they'll build a shroud around them. And so it's like, but the air is just open to come in. So I mean, you're not controlling that air at all. And then you got these guys here, thermal oxidizers. I think we can all pretty much understand that those are not flares. But the big thing was when the NSPSJA came out and it made the flare an affected facility, people looked at their permits and said, well, I have this thing in my permit, it's called a flare. You know, is it truly a flare? And so that's where, you know, we want people to, if you have these vapor combustors, is you may, if they're called a flare in your permit, you may want to think about getting that name changed, just to remove that kind of confusion from your permit. So how did flaring start off? I mean, at the time, there were no flares. And people, when they had vessels and they overpressured, they would vent to atmosphere. Well, that caused a little problem is because you now have a nice vapor cloud in the middle of your process unit, which is likely to combust and cause a lot of fires. So people decided that was a bad idea. So then they said, okay, we want to get those combustible materials away from the process unit, away from the people. So then they start off with a lot of these pit flares, where they just had everything run in a pipe, dug a hole. You know, they had some gases or liquids, even liquids that they wanted to get rid of, send it out to the pit, torch off the pit, you got rid of your stuff. These flares, while not so common in the U.S., are around the world. You know, it's still in use today. So I mean, it is, especially on like some of the upstream side in some other countries, that this is still a practice that is in use today. But what would you say if you saw that guy? That looks like it's around today. This is a picture of a flare, a ground flare, pit flare that is in service today in the United States. So they a little more complicated than just that pipe run into the hole, but it's something that is still here. They're very rare, but they are still around. So the biggest thing that when flares came about is they were installed as safety devices. That was their primary purpose. And so, you know, you have to always understand that about flares. It's like they you know, their primary purpose is safety. And we can't not say that enough, is that, you know, when people start saying, you know, how much can you control this flare, you have to understand that it needs to operate over a wide window of flow conditions, compositions. It has a very unique purpose. But the issues started changing because in the beginning, you know, it was better to flare than to just release, you know, potentially toxic, you know, hydrocarbons out into the atmosphere unburned. So it was better to combust them. But then kind of the world changed and everybody started riding everything to their flares because that's great. You know, we have this gas that we don't know what to do with. Let's put it to the flare and then it's controlled. So then, you know, we're doing the right thing. But it's this low flow cases that seems to have really started to cause a lot of the problems. So it's like when a flare's going like this, you know, it's operating as it should. I mean, it's getting great combustion. Yes, it is smoking, which is not desirable, but, you know, that is good combustion. So it, you know, but it is, when you drive around, I don't know how many of you have been to Houston or Texas City or anywhere, you know, you're going to see a ton of flares. And how many of them do you see flames on top of? Not a lot of them. I mean, most of them you barely see anything coming out of them. So at that low case, are you still getting the combustion you need? And so that's where a lot of the EPA allegations have come forth, where they feel that no, you're not getting that control. So when you're thinking about flaring, the biggest thing is you know, the flare is designed because, you know, you got, say you lose, the worst case, you lose power at the facility, all of a sudden all your relief valves blow, boom. You got to get rid of a huge volume at a rapid pace, because that's the whole thing is, you have an upset condition, it's usually, you know, a high pressure, high temperature situation. You need to get that material out of the vessel, because otherwise it's going to cause problems with the vessel and just, you know, potentially explosions, equipment damage. That is a, you know, usually it's cheaper to vent the vessel and burn off all the contents than to cause damage to the vessel. So I mean, you definitely need a way to get that material out of there. You know, and always this, you know, getting back to the safety device, you also want to bring that combustion away from people and equipment. You always are you know, want to do this. And, you know, also the nice thing about having a nice tall flare, it also aids in dispersion, so, you know, you get an added benefit from that. You know, a lot of people, you know, thought about flaring and saying, you know, you think the allegation is that everybody's flaring a ton of material. And I don't see that there are some cases where, yes, people are maybe flaring more gas than they maybe could. But a lot of times, you know, the flare, when it's got a big flame on top of it every single day, doesn't take long before everybody at the plant starts saying, that's a lot of lost energy. You know, what is that material? Is that lost, you know, is that raw material, lost product? I mean, everybody starts equating that flame with dollar signs. So there's already been a huge push for people to minimize that amount of flaring just because of the dollar value of that gas. But then it also, we had this shift of, we're going from a safety device and we start moving to the environmental control device. And that's where you really start getting into the EPA concern, because, you know, you have the general duty clause to operate things in accordance with good air pollution control practices. So, I mean, that's where you really start getting into the scrutiny for flares. So, back in the 80s, so I mean, that's in the past, but not all that far. You know, this is kind of where they started doing a lot of testing around flares to see, you know, what kind of combustion efficiency are we getting? Because, you know, anytime you have a control device, you care about the amount of control you're getting out of it. You want to use that combustion efficiency in your permitting to say, look, oh, well, I had 10 tons of material going to the flare, but coming from this process, but I sent it to the flare. So now how much actual emissions is coming from that unit? So, you know, that amount of control was definitely something people wanted to know. So that there was a lot of testing done. Some on little tiny lab scale flares, some on big industrial flares. It kind of ran the gamut. But again, it was, you know, I kind of think of it as the beginning of the learning curve. It's like, you know, people got to try to isolate certain things to try to figure out, are there governing equations or governing operating conditions? But we got a rule. We got CFRs 60.18. If you haven't read that yet, it's a short read. We'll talk about that later, but it's one of the rules that covers most flares. Once your flare is subject to an NSPS, you're into the 60.18 ball game. But it basically has only a few requirements. One of the biggest ones is the no visible emissions. Don't smoke your flare. Everybody knows this one. Everybody lives by this one. You go talk to the operators, you say, how often do you deal with the flare? And their answer will be, well, anytime it smokes. If it's smoking, then they're dealing with it. If it's not smoking, they're not dealing with their flare. So it was something that it was there, and they touched it every so often, but really they don't think about it on a day-to-day basis. The studies also showed that you need to have a certain amount of heat content in the vent gases going to the flare. They showed that for assisted flares, for steam and air assisted flares, they decided on you needed to have at least 300 BTUs per scuff in the vent gas going to the flare. And then they said, you know what, you can't get the flame going so fast that it's basically going to lift off and potentially blow out and blow itself out, that you need to keep that tip velocity generally below 60 feet per second. We'll talk about some variations to that limit, but that's the number that pretty much everybody has on the tip of their tongue, is less than 60 feet per second. And an easy way to think about that is you want to give that material, it's kind of like residence time in a thermal oxidizers. You want to have enough time in the combustion zone for that combustion to actually happen. Usually the lower heating value. Yeah.
How do you define the combustion efficiency? You say 98% CE. How do you define it?
We'll actually show you the equations later today, but it is combustion where you're going all the way to carbon dioxide and water. So that's going to be a distinction too, that we'll use the words destruction efficiency and combustion efficiency. We like to kind of almost interchange them a lot. They are different, and they have different impacts in the rule. So we'll get to that, but it is definitely a good thing to think about. And then we always like this one is, how many people at your facility would allow somebody to get to do that? You know, we say, well, people say, well, they got the thermal suits on, and we're all like, well, have you seen the Jiffy Pop popcorn? You know, the old little aluminum things, and that, you know, the wind shifts, and they're having a very bad day. So yeah, this is I don't even know where we got this. Yeah, we got it from flarestacks.com, but I don't even know that facilities would do this today. The safety guys would have a nightmare. So back, show you some of the different flare studies, and we're not going to talk about all these flare studies. Don't, that would take a whole day, and we're not going to go into that level of detail. But there's just a few ones I just want to point out a couple of different things about these studies to kind of show you where the knowledge came from. And one of the things to think about here is the flare size. You know, this is the tip diameter. And you see, wow, they got all the way down to just a 0.5 inches. I mean, that's a Bunsen burner at that point. I mean, so that's, you know, how applicable are some of these studies to large industrial flares? Because, I mean, we were talking to people yesterday that had, I think their biggest flare was 82 inches. So that's like this tall. So if I can fall through it, you know, it's a lot different than a Bunsen burner. But I mean, that's kind of what they could do. That was the only way that they could control the experiments to get the data. One of the ones we like to talk about here is the Siegel study. It was a German guy in Karlsruhe, Germany. He was actually doing his PhD thesis. So he did some interesting things, and some of the things we like to talk about is one of the things that was different here. You see, everybody's using like nice mixtures of gases. He actually used refinery gas. So he actually was at a refinery and was using that variable gas that was coming from the process. And one of the things, and so, you know, so that was nice. And one of the things he did was he set up an array, you know, that was basically a field of little pitot tube sample ports. And then he took a fan and he got it so he could blow across the tip of the flare to blow that plume into his array. So then he could collect all the samples. It was over 2,000 samples. And then he ran those all through the GC to figure out what was left over from the combustion. Took samples of the refinery gas going in, measured the ones coming out. Of those over 2,000 points, all but 4 had 99% destruction efficiency. So the 4 that didn't have 99% had 97%. So one of the things he was able to show was, yes, using a real flare, using real refinery gas, it is possible to get very high combustion efficiency out of a flare. So, and generally that's what you can see here, is that, you know, you can get good combustion out of a flare. And so it is a viable means of using it as a control device. Some of the lower ranges here, I mean, just through the test parameters, they're going to take these things down to very low BTUs, you know, barely burning flares. So I mean, the data varies, but we did get nice. They were able to show pretty much in every case that yes, you can get good destruction efficiency. This is a chart, and we drew the red line on here because we got tired of telling people that there were points on there that you couldn't see. But this study here, and it's really funny, is one of the guys who was involved in this study is at this conference. He's up in the flare experts room, so that was a little intimidating for me to be talking to the room about these studies, and the guy who did the study was sitting in the room, so that was a new dynamic for myself. So it was interesting. But one of the things that it showed was on the bottom here, it's really hard to read, is steam to vent gas ratio. So how much steam you're adding pound per vent gas that's going there. And on this side is the combustion efficiency. And what they saw was as you start increasing that amount of steam that you're adding to the flare per vent gas, suddenly you hit a point and that combustion efficiency will plummet. They've shown this time and time again that you have this window where you can get really good combustion efficiency, and then you just fall off the cliff. And we like to show this graph for one important reason, and that is if your facility ever got into an enforcement situation, there is someone at the EPA who likes to show you this graph to show you how you should have known about oversteaming. That's kind of where these allegations come from. This data, these studies, have been out there since the 80s. You know, how can you say, well, we were operating the flare how we were supposed to when you were grossly oversteaming your flare? The studies are out there. Yes?
What's the benefit to injecting steam?
It adds air. It adds turbulence, mixing. It's for knocking down the smoke. So I mean, when a flare is going and you got basically not enough oxygen in the combustion zone to go to full complete combustion, that's when you get the soot formation and you get smoking. And so they discovered that if you inject steam, that helps add turbulence, induce that atmospheric air into the flame zone.
The operators go to stop the smoking when it occurs?
Yeah. I mean, they'll have a steam valve, and you know they see smoking, boom, they're turning up that steam. Sometimes that is the only control that an operator has over control of their flare. They have one valve, a steam valve. So I mean, it's very limited control, because again, they can't decide how much gas is going to the flare. It's going to relieve for a whole variety of reasons. So I mean, they got steam or air, and sometimes not even that. They came up with these numbers in the report that basically said that data suggests steam to gas ratios from 0.4 to 1.5. So that's way back here in this zone. They did have some data points right here, and that equates to about the 3 to 1. And you'll hear that number again. One of the things is a lot of the numbers from EPA are that 3 to 1 ratio. That's based off of, I think there's 2 data points there, and that's where that came from. So you just got to understand that yes, there are studies, but there isn't a ton of information out there. Okay, so they did all these studies, and they decided yes, you can use the flare as a control device. They talk a lot about flame stability. And if you have a good stable flame, you're going to get good combustion. One of the things though is they don't define flame stability anywhere, other than the fact that you have a flame. So if you have a flame, it's a stable flame, because obviously if you don't have a flame, you're not getting good combustion. So, but they like to use this word a lot, because you know they'll say things like you want to have a nice, upright, luminous flame, maybe with a little bit of black marbling in there. That's where they're saying they're going to use all these words to kind of describe a well-operated flare. But they're all nice subjective words that, are all interpretation. So it's an interesting place. From the, they definitely say that it's this stable flame is dependent on the flare design and the gas composition. So they understood that, it is going to depend on what you're sending to your flare is how good of combustion you can get. Again, concepts that we already talked about, the gas exit velocity is important, heating value, and so then it's again, flame stability. I can't talk this morning. But they really wanted to say is you need to think about the heating value, but this composition can definitely affect your flare. Okay, so here's some of the more things from going into more detail on NSPS Subpart A 60.18. And one thing just to remember for your flares is just because you have a flare at your facility doesn't mean that it's subject to 60.18. You are brought into the party by using the flare as a control device for another NSPS regulated affected facility. One of the big ones is LDAR components. Under VBA, VB, GGA, you have, instead of monitoring some of these devices for LDAR, you route them to the flare, they get controlled by the combustion device. Welcome to 60.18. You're in the game now. And that's just one example. But that's also when you get into enforcement, that is one of the things that EPA will have you do, is tell you, are you using your flare as a control device for these other regulated entities to kind of build that case of you were subject to these rules, you should have been complying with these rules. Now we always said, have a flame present at all times. We have a lot of discussions about this. Is which flame are they talking about? Because one of the things is, yes, you have to have a flame, and then the very next section says, okay, well, to show you have a flame, you need to have a pilot with a thermocouple to show. So is it the pilot flame you're thinking about, or is it the big flame? And, depending on who you talk to, they will argue, sometimes quite vehemently, either way. We generally like to say, though, there's a difference between passing a 300 BTU per scuff stream near a pilot or passing a 300 BTU scuff through a combustion zone. So, I mean, it's definitely, you can have pilots up there and you may not be getting the combustion. We got the 60 feet per second. One of the nice things that they did identify was this here statement. You have to operate the flares, but only when you're sending waste gases to them. So it's nice that they said you don't have to comply when you're not sending anything to your flare. Some facilities this becomes more pertinent than others. There are some facilities that these flares are only used for very rare occasions, maybe a startup, maybe a shutdown, worst case emergency. So that they want to have some variation in how they comply. But when waste gas is going there, you need to comply. They also added this thing that you have to follow 60.18, but if another NSPS gives you more requirements, they're allowed to do so, and then you have to follow those requirements. It wasn't until NSPS-JA came out in 2012 that any NSPS gave you any additional requirements for your flare. So just know that we spent 30 years with no rule saying anything more on flaring. People always ask, is there any performance testing in 60.18? The words performance test never show up in 60.18, but they do have an equation that has a footnote that basically says that you have to determine the net heating value to show that 300 BTU per scuff. You have to determine that using the method 18. So that's where you're getting pulled into doing some sort of testing on your flare. So they don't come out and say it. Okay, so fast forward a few years to the 90s, and this is kind of the moment that all permit engineers were waiting for, because this is what we really needed. And one thing it gave us was, it gave us the number. What's the number I can use in my permit application on my emissions calcs to claim a combustion efficiency for the flare? And we got it. We got 98% combustion efficiency. One of the things that was kind of interesting, though, was they start off the flare section, and they say noise and heat are the most apparent undesirable effects of a flare. Did anybody see noise or heat in 60.18? I didn't see it. I mean, it's like, okay, so why is noise and heat the worst thing coming out of a flare? But and we don't care about it in the rule. So that's interesting. Another thing that it goes on to say is emissions from a flare include soot. Well, I thought we were supposed to be smokeless. It said no visible emissions. Well, soot's going to give you visible emissions. So already the AP 42 section says that the flare is going to likely give you visible emissions. So,
Should be good from burning coal, right?
I mean, it's just the unburned hydrocarbon. So that's just, there's a lot of different chemistries going on up there, but it's just formation of soot particles. It tells you also, you know, you will have unburned hydrocarbons. So yes, you can't go all the way to 100%. NOx, SO2, actually they are actually revising AP 42 emission factors for flares right now. There's a lot of controversy over the NOx number. They used, people have a lot of issues with a performance test was done, so now they've significantly increased the NOx emission rate. Even if they throw out that data point, it's still a significant increase, but hopefully that one data point will be removed. It also talks about, you know, in this, if you have sulfur in the fuel going to the flare, you're going to have SO2 emissions. That really comes into play with NSPS JA, which we're going to talk about in detail later this afternoon. Talks about, and another thing is that it talks about the extent of combustion, talks about the rate and extent of fuel-air mixing, and on flame temperatures. Again, was there any temperature in 60.18? No. So again, they're telling us in AP 42 how they come up with and what they decided was important for determining emission factors, yet that's not in the rules. So you kind of start to see, and where you'll see this a lot, is that the rules don't fit exactly for flares, and that's where a lot of this confusion comes from, is that you're applying rules that are very hard to apply to a flare. So here we can show you those revisions. One of the things that just when I saw this, I had to take a moment, just because they kept noise and heat, but then they added a visible flame is undesirable. How are you supposed to get combustion without a visible flame? This is one where you're just like, people have lost grip on reality. And no, but you know where it comes from, is if you have a facility with a flare, what is the main thing that your neighbors are going to complain about? The flare. They hate seeing, especially if you're in an area where you had, especially in this is an issue in California where you have these refineries that have been there forever, and suddenly the homes moved in, so now they have neighborhoods around these refineries, and people are saying, we really hate seeing that flame at night. We don't like the flickering in our windows. So can you please knock down that? Can you guys get away from that flare? And so, you know, that's where I think that visible flame came in. But it's hard to tell people that you like that flame. You want to see that flame. That means you're not getting exposed to all these nasty hydrocarbons. But you know, that's public outreach. That's education. They changed from 98% combustion efficiency to destruction efficiency. So this is, we'll talk about this later today. That's a key difference that they've started to talk about. And so taking out the CO emissions. Oh, and I didn't show you before. We like to put in here that they also misspelled emissions in the rule. So, you know, maybe they didn't have spell checker back then. I don't know, but they fixed it. Okay, so that was the NSPS side. We also have a similar one on the MAC side, Part 63.11. It is almost word for word identical to 60.18. So we're not going to spend a lot of time on it. Has all the same parameters, no visible emission, flame present, all that good stuff. And it also says, you know, other applicable subparts can add additional requirements. And that's what we're seeing coming out with MAC-CC, is that's where all these new requirements are going to come out. Okay, so we're talking about smoke. And everybody hated smoke. We wanted, you know, mainly for PM emissions. Don't want to have a smoking flare because you can put out a lot of PM emissions. That necessarily doesn't mean that that flare is not getting a good destruction efficiency, but it is smoking and it's undesirable. So, you know, there are methods, method 9, method 22, to determine how much smoke is coming off your flare. You know, method 9 is a more rigorous, you have to become certified. Method 22 is you just become trained and knowledgeable in looking at smoke. So, you know, they come back and they said, okay, we got these, you know, they even had the charts, the Ringelmann scales to say how much. So you got guys out there with a piece of paper, they got the smoke, they're looking at to figure out how much smoke are they putting out there. But then everybody says, okay, what's the solution? Steam. Steam is your solution. It helps get rid of that smoke. So everybody's going to say, you know, that's where we get into that turbulence. And this is actually a pretty big flare. Inside here, you see these tubes here. Those are called lower steam injection. And actually, the air inlets are down here in the base of the tip. They're going to come in, mix with steam, go up, have air, induce air, and come up and add that steam and air into the center of the combustion zone. Generally, you only have that when you get to the much bigger flares. But then, you know, there's also, instead of steam, they also found you can just add air. Works a little different, but the same principle. And we like to always say, it increases greater combustion efficiency because you're getting rid of the smoke, so you're going all the way to carbon dioxide and water. But there's a point to that assist. You can get to a point where you're adding too much assist, and now you're actually decreasing the combustion efficiency. So let's get into a little bit more recent stuff, just to say that, you know, we're not always thinking about all these studies back in the 80s. We're going to talk about TCAQ air quality study in the HRVOC area, the Houston-Galveston area. It's a non-attainment area for ozone. They have some special rules there. We'll talk just a little bit about California, just because they went kind of, you know, it's that whole thing, how goes California, so goes the rest of the country, at least for environmental stuff. That's somewhat true. There's been some breaks from what's happening in California with the rest of the country. We're going to talk about this case here in Addison, Ohio. This was the landmark flaring case that basically showed EPA that there was a problem, and it was a widespread problem. So we'll talk in detail about that. And then as recent as 2011, TCEQ again did a test at the John Zink facility in Tulsa, Oklahoma, where they actually did testing. Again, they redid a lot of this testing on actual industrial flares, not 200 feet up in the air, just the tips mounted at the ground level, but they did a lot of testing around that to understand this, how much assist you're putting to your flare and how that affects combustion. So, the big thing in Texas came from, they were trying to get the emissions inventory data to meet their models. You know, that's always the goal of a regulatory agency, because they use these models for their SIP planning to come into attainment. So they wanted to try to get their models working with the data they had, because everybody's got to submit their emissions inventories. So they should know what's coming from the facilities and what the model should say. So there was an event, and on August 30th of 2000, where they had an event at a facility, and downwind of that facility, they had air quality monitors. So they got the data. The company who had the event submitted an excess emissions report, told them how much they emitted. And so they said, okay, let's see if we can get the model to match the data. So here's a picture from the flyover. And actually, it's kind of hard to see, but there's actually 3 flares at this site. There's the one guy you can definitely see. It's the tall guy here, and you can see that the tip's way up here, and that's the one that's smoking. You got another one here, a little shorter guy. It's you can see the nice big flame on it. But what we've been told is there is actually a 3rd flare, and it's this guy over here. And one thing, what do you not see on top of it? There's no flame. So the thought is that this guy, and if you were to say, if you were to look at this picture and say, which one has the most emissions? Well, I'll say, which one's causing the problem? What would you say? Yeah, the first thought, everybody's thought is that's the troublemaker. But actually, we're thinking it's more that little guy with no flame on it that's having the excess emissions, because a smoking flare is having, combustion is occurring. So they went back and they ran their models, and they came to a conclusion, and that was that based on the data that they were given from this event, where you're going to have the emissions coming from the flare, they could not get the model to match the emissions unless they decreased that combustion efficiency from 98 to 90%. And this was kind of where they were saying, wow, this could really be a problem. And Russ Nettles from the TCEQ is here at the conference, and he works with the emissions inventory. So I mean, if you talk to him, he's a nice guy. They did a lot of work, based off of this and trying to understand this, and he'll talk about flares that are over assisted and how they can they can sometimes as much as double the amount of emissions going into an area if they're not properly operated. So out of that, we decided, well, this is an issue. We need to do something because they need to come into a compliance with the NAAQS. So we get the HR VOC rules, the highly reactive VOC rules. So they said that they wanted to really focus on certain VOCs that are more likely to create ozone at ground level. So one of the things that they did was it caused everybody to install flow meters on their headers and install composition analyzers to understand what's in the vent gas. So this is really some of the reasons why today, when the new rules come out and everybody needs to put flow meters and analyzers on their flare, why we have ones to choose from, because they were forced to do it back in 2003. Because flare service is a lot different from a lot of other services, so you've got some hurdles to get through for those systems. So this was really how they went through that learning process with the instrumentation. Okay. California, they kind of went their own way because they really wanted to get rid of, they just don't want flaring at all. They want to remove flaring totally. I mean, that's their desire. So there's been a huge push, and they have their own, and you know, if you don't know about California, they have their own air quality management districts, which will regulate that air shed separately. So you have some of the three big ones for the Bay Area, South Coast, and San Joaquin Valley. So they were regulating flaring before like NSPS-JA came out. There was actually, when NSPS-JA came out first and before it got pulled back, it actually had a lot of things that were in the California rules, namely a 250,000 cubic feet per day flaring limit. So in California, they put a hard limit on flaring. Luckily, when JA got finalized, the rest of the country did not get that hard limit. We got a range to operate in. But so they were really against flaring. And how have the refiners in California dealt with this? Every single one of them have installed flare gas recovery. So now they're all have these big compressors that are sucking back the gas and keeping it from their flare. So I mean that regulation basically drove them all down a path. But so you know, just be aware that certain states have more stringent requirements on flares, but not all of them. Okay, Lanxess, Ohio, or Lanxess in Addison, Ohio. This was the aha moment for the EPA. This is up in Region 5. There were two guys, Brian Dickens and Pat Foley with the EPA, who were the ones that were investigating this. Pat Foley is still highly involved with flares and flare enforcement. If you get into a consent decree discussion, Pat Foley will be in the room. So just know that he's been there from the beginning. So what the deal was you have this facility in the town. They were a source of butadiene, acrylonitriles. And what did they have across the street from the facility? An elementary school. Maybe not the best place. You know, probably one of those things where the company maybe even gave them the land to put the school on, you know, one of those deals. But what was sitting on top of the school? An air quality monitor. And all of a sudden, what does the data start showing? We're starting to have a lot of these high butadiene episodes. And so, you know, of course, we're going to be highly concerned about this. So EPA goes to the facility, and this isn't like it's in Texas City where there's a ton of chemical manufacturing. This is it. They looked through the whole town, and there were no other sources of butadiene and acrylonitrile. So I mean, they made sure that it wasn't something else. And the EPA came in, the facility spent a huge amount of effort, amount of money, scouring this facility, trying to find the source of the butadiene. You know, everybody is just, you know, they want to find the problem. They're out there, they have the FLIR cameras, they're looking at everything. They can't find it. Then somebody gets the idea of saying, I wonder if I lift the FLIR camera up. And guess what they saw? Nice big plume. And where's it coming from? It's in the channel 9 footage. It's the nice big flare right there. And what's not on top of the flare? No flame. When they looked at where the steam was controlled, they were assisting the flare at a 500 to 1 steam to vent gas ratio. 500. And we think 3 is the maximum. And the question was, well, how did that happen? You know, why was that? And the thing was, you know, they had a community action group. You know, they talked with the community. You know, they want to say, what are we doing? What can we do better? What are your complaints? And what was the complaint? The complaint was, we hate having that flare. We hate seeing the flame. And they're like, oh, that's no problem. We can knock down that flame a little bit. We'll just turn up the steam. Knock down the flare. Like, yeah, you know, that flame. We still hate that flame. Suddenly, boom. They got that steam assist up to 500 to 1, and there's no more flame. Nobody's complaining anymore. But, you know, that kind of was the problem. And then, so the EPA, they said, okay, well, this is surely a unique case. We're not going to go, no, not everybody's doing this. So they could start going around to a lot of the other different chemical and refining industries in Region 5, and they basically said, no, this is a widespread issue. And so that's where this whole ball started rolling. I mean, when you saw the first flare consent decrees, they were all coming out of Region 5. So what does, hold on, let me, okay. So what does success get you? Success gets you money. Money to then go and train people in all the other EPA regions. So now there are people from every EPA region that have been trained on this issue. And, you know, about the time that they were doing this training, not soon after, we started seeing a lot of 114 letters rolling out of the EPA. And not just, a lot of times they were coming out of, you know, the headquarters in Washington. And now we start seeing them coming directly from the EPA regions. So it's definitely something that has become a hot button issue, and people are getting these 114s. We'll talk about 114s kind of at the end, but if you get one, don't wait. Start working on it immediately. We run into that a lot, is that they have a very short window for data gathering, and you're going to need every second of it. But we'll talk about that more later. So, you know, the focus was on visible emissions, no smoke, so add steam. We basically started saying, okay, we know that through the testing that we can get 98% control efficiency. Got a regulation to help us operate it properly. We see different states, you know, kind of going a little bit farther, maybe putting a little other regulation, some other monitoring that they need to do. Definitely start understanding this thing that the flare could be a significant source of emissions. The Ohio case showed that a flare can be easily oversteamed. And so they basically said, okay, we got this data now. We need to run these tests again to determine, you know, it's been decades, you know, technology gets better. Let's do these tests again. So they did some testing, like I said, at the Johns Inc. facility. They did it on both an air-assisted flare, you see here, and a steam-assisted flare. And how the test was they send a lot of gas mixtures, different BTU contents at like the same flow rates, and then varied the steam addition to kind of understand what was that interaction between BTUs in the vent gas and combustion efficiency. I think we have pictures later in the presentation. We'll show you how they actually got this data. But one thing you can kind of see here is, you know, you see this flare, you know, pretty relatively, you know, 350 BTUs per gas. That's not a huge amount of energy, but you know, it's above what they needed. You know, down at 0.29 steam to vent gas, what do you have? You have a nice luminous flame here, and they're measured 99.2% destruction efficiency. So then they go and they say, okay, they almost doubled it. You're still really low, 0.5 to 1. I mean, that's a pretty low steam to vent gas ratio, and already, boom, you're down to 90%. So you're away from your nice 98. Then, just barely, not even double it again, wham, you're down at 27%. And some would say you almost get to nothing eventually. And what don't you see? No flame, only steam. So, we go around and we've seen a ton of flares. You see a lot of flares that look like this. And so that's something that people need to be aware of is, you don't see a flame up there. But I also like to caveat that with, go look at your flares at night. I've been to plenty of facilities where I'm looking at them, I go, oh, I don't see anything. Well, when we're driving back from dinner, we'll drive by the facility. That's what I do for fun. I drive by facilities at night and look at their flares to see if they have a flame going. And a lot of times, you know, if you get mainly pure methane, or if you have, especially if you have a lot of hydrogen, you can't see the flame. But at night, you'll have a blue flame up there, and so you can see that yes, there is actually gas going up there. Because one thing that you know, you learn is hydrogen the flame is invisible. So just so everybody's aware. They spent over $2 million doing this study. And that doesn't include all the time that was donated by all the professors and people that were involved in this study. This was $2 million is a very low estimate. And what did they learn after spending $2 million? If you put water on a fire, it goes out. So just remember that money was well spent.
I guess if you have a plant that doesn't have steam,
Yeah, usually you're into either an air-assisted or unassisted flare.
right.
So I mean, they have air-assisted has. We'll show some graphs from air-assisted flares. They follow a similar trend, but it is slightly different. Unassisted flares, pretty much, you don't have to worry about it.
Right. But it's natural gas processing plant products that have steam.
Yep. Yeah, and you even get beyond that. We'll talk about this cool thing called pressure-assisted flares, and then that has some rather unique benefits to it. Okay, so this is where you kind of need to kind of shift. Yeah, the Texas study started to shift how you thought about your flare. When you were thinking about 60.18, you were here. You're thinking about what's the BTU content in the vent gas going to my flare. Well, what happens was through these tests, you start moving up the pipe until eventually when you're talking about consent decrees and now the proposed changes to max CC, you're up here. So you're now going to be concerned about the net heating value, not only of the gas that's going to your flare, because that requirement's not going away. But you also have to care about what's the net heating value after you've added your assist gas. Okay, so how many people in the room got one of these? I'd just like to see if anybody got one. The enforcement alert came out. Basically, they were saying that people weren't. Basically, the EPA was kind of upset that more refineries did not take up subpart NSPS-J applicability. NSPS-J came out and flares were covered under that as a fuel combustion device, had SO2 limits, but through a lot of hand waving, people said we didn't trigger it. So the EPA said, oh, okay, well, you know, we still think that SO2 emissions are too high, so they decided that they were going to get a new rule, and that is where NSPS-JA came out, which is going to pull in probably every refinery flare in short order, if not already. Then again, we got another enforcement alert, this time on oversteaming. Basically, this letter went out to every refinery, and I think we said it was like over 100 chemical facilities. We tried to FOIA the EPA to get that list of people who that alert went to, and just because we're consultants, we like to have clients, so we thought these are people that might be concerned about their flare. But what the EPA said, no, we cannot give you that list. And they said it is because it is part of ongoing enforcement. So does that mean that anybody who got that letter is suddenly in the enforcement game? that's a interesting take on saying why they couldn't give us some information. So just be aware of the things that they're saying. And then we got back and they announced that, okay, one of the EPA's national initiatives for, we're right in the middle of this time frame, is flaring. So just so you know, right now there is a lot of focus on flaring, and maybe not a lot of fun, but we like to have that here in the class. So, but yeah, so it is something that is very interesting. Okay, so just in case you're not aware, EPA, when they want to do or write a new rule or make amendments to a rule, they need data to do that rule writing. So what they do, and they did this back for the refining sector in 2011, is they sent out what's called an information collection request. A whole bunch of questions that every refiner had to respond to. Took a lot of effort, a lot of time, and they got all this data. And basically now, that was in 2011, what did we get in 2014? We got the proposed changes to max CC. So we see that they got data, they're revising the rule. If you are in the ethylene industry, the ethylene ICR is just, I think it just got over. So they have now collected up a whole bunch of information on the ethylene industry. So we're expecting that, I think the latest we heard was maybe June. June was for Mac. We're anticipating that in the next year or so, we're probably going to see proposed changes to the ethylene MACT. So we're expecting that there to be flare changes in the ethylene MACT. So it's coming. But we looked at the data. This data is all, we FOIA'd it, got all this data. I think, yeah. One thing with the information collection request was there was different levels for different facilities. Some people just had to answer some questions. Some people had to do some sampling. There were some performance tests done. It was kind of, it just depended on who you were as to what you had to do. But it gave us some nice statistics. At this time, there was 149 refineries in the U.S. with 507 flares. Now that number, it's still in the ballpark. We've heard of a few new flares going in, but they have been taking some flares out of service as well. So it's still in that same ballpark. And this is just refining. There's probably 4 times as many flares in the chemical side. So we looked at the data just to see, because we're concerned about just how many, what type of flares are out there. Are they steam assisted, air assisted? What's the assist type? How are they doing these various things? So we found out that a huge portion of the flares out there are steam assisted. So I mean that tells you that most people they went with steam assisted flares. Or wait, no, this is elevated. Sorry, getting ahead of myself. Elevated flares. Most people have the big stick in the sky. Some of them have elevated pressure assisted type. We'll talk about those later. We do have a small amount that are ground flares, either the pit type or there's another pressure assisted type that's kind of a big field. And then other. And we're always, when you do an ICR, you don't always have an answer that, because it's a database, so you don't always have an answer that fits nicely into their choices. So, there were a couple others, or maybe there were a couple of vapor combustors added in there. We don't know. So the assist type, we found out that a huge quantity of flares are steam assisted. Air assisted is the next biggest group. A lot of some unassisted flares. I mean, those happen. And then again, other, which we were wondering maybe that was somebody that was saying it's pressure assisted. Generally, pressure assisted flares are, kind of a hot topic right now. What we've seen so far is that the EPA is sticking to this 3-tiered classification system. So a pressure-assisted flare, while it gets no steam or air added to it, they call that a pressure-assisted, unassisted flare. So they're still calling it an unassisted flare. How do you keep your pilots lit? Remember, you got to have those pilots at all times for NSPS or 60.18. Almost everybody says they have a continuous pilot flame. Few people have the spark ignition. And so that's different from pilot ignition. So that's not how you light your pilot with a spark. That's how you light the big ball of fire, is with a spark. Just to keep, because we'll talk about that later. And then they also have this one, spark ignition triggered by flow. So that gets back to that whole concept of you don't need to have these flames when there's no waste gas going to it. So if you have a system where you have some monitoring to say, okay, now stuff is going to it, it'll start sparking and it'll combust the gas when it reaches the tip. Okay, so how often are people using their flares? So I mean, we see here that there is a good number of flares out there that are combusting their flares, having gas going to their flares a lot, most of the time. So I mean, there are flares in constant use today. You have another, the various slices. You have some flares that combust gas only during startup and shutdowns. We do see that case, just a small number of them. Only during upsets. I guess you have to get into that discussion of what is an upset. And then, so only startup shutdowns or upsets. So there is definitely, a slice of the pie where, where people aren't, doing, having routine flaring. This was just kind of more data that they gave to us, trying to see, what kind of reduction things people were doing. Because there's through NSPS-JA and the consent decrees, there's been this shift towards also thinking about minimizing your flaring. Some of these kind of are interesting, just because you have best management practices to reduce NOx. We don't know what that is. We like this. There are 100 as of this time. There were 159 out of 500 that had FGR systems able to capture 100% of the vent gas. So I mean that tells you that it is feasible. I mean the people are doing that, so you can't just say it's not possible. But there's other economics to think about. Or you have FGR, but you're not going to be able to capture the flow in all conditions. We see that as well. It was 2011. Flare management techniques, again, people, they provided a whole bunch of different management techniques. A lot of people like to, do the little root cause analyses. A lot of that's, from consent decrees. It's a very similar process now in NSPS-JA. Just to look at why you flared and how you can make it not happen in the future. I don't know how having a simplified PFD of the flare system is a real management technique, but okay. So that was my maybe not so brief introduction to the world of flaring. Next, we're going to talk about components, and then you can see we're going to kind of talk about combustion, how you monitor that combustion, how you try to control that combustion, and then we'll get into some of the rules, and then we'll kind of finish up today with thinking about enforcement and kind of our path forward. So, so Rashab's going to take over now. We have a half an hour till the first break, so we can probably get through. Nope. They didn't put these in order. Don't put it too high.
All right, good morning. Can you guys hear me? All good? All right, so, you know, just want to start off by introducing myself. I'm Rishabh, and I work out of the Sage Atlanta office. And, you know, we've been doing flares for about 2 years now. Just, there's so much out there to do, and we really enjoy it. Some of the facilities we work at, they actually refer to us as the flare nerds, so so I'm one of the nerds, just to introduce myself. And you know, so we've kind of started off the day with the general regulations, and by now we all know having a flame present on top of a flare, that's a good thing. Over-assisting, not such a good thing. Smoking, not the best. So now we're going to kind of get into how a flare system works. And we'll start off with components, and a lot of you might already know some, you know, the components that we're going to talk about, so help me out as we go along. And yeah, so let's get into it. Okay, so the path we're going to follow today is we're going to start off upstream where the flare gases actually originates at the process units, and then kind of go downstream all the way to the flare stack. And we're going to break it up into the physical components that make up a flare system, as well as the gases such as the vent gas, the supplemental gas, your pilot gas, ignition gas, and so on. Okay, so we'll start off with the process units. That's essentially where the vent gas originates. You know, process units, they work in different ways, and they're usually at a steady state, but occasionally they can overpressure, or you can have an upset, you can have a power outage that leads to high pressure, high temperatures, and the flare basically serves as a device that can help control those excess flows coming from the process units. So instead of venting those toxic hydrocarbons to the atmosphere, you want to send it to a flare where you can combust it and make it less, you know, safe to release. There are many different types of contributions that go to a flare. You have your control valves, pressure-sensitive valves. You have manual bypasses, your manual valves, restriction orifices. So there's many different ways in which you can be tied into your flare. And you know, that's actually one of the things that the regulations require, is for you to make a list of all your connections to the flare, which we'll get into later. Sizing you know, you have to anticipate how bad a power outage or an emergency event can get and how much your flare can handle. So that's something to take into consideration when you're sizing for your flow rates. The vent gas itself, you know, generated from the process units, and it's highly variable. So you don't always have a consistent, constant flow that, you know, you can predict all the time. It's always changing. Sometimes all you can have is your sweep gas or your purge gas, and other times during an emergency, you can have a whole range of different hydrocarbons going to your flare. So it's very variable, and if you want to be able to control your flare the way, you know, if you want to make it work right, you have to also then monitor what's going to your flare, and that's when you get into the composition monitoring, sulfur monitoring, and just the volumetric flow or mass flow going to your flare. So we'll get into monitoring later on too. All right, so the flare gas header, it's usually that big pipe in the refinery that you see running across. It essentially serves the purpose of collecting all that vent gas and directing it to the flare. They're hard pipe connections, and one of the most important things you'll hear, you know, all throughout the day, but is the potential for oxygen infiltration into your flare header. That's something you want to avoid, you know, because if what's going through your flare header is a combustible mixture, and if you add oxygen, and if there's a spark by any chance, you know, it could go kaboom. So that's something we want to avoid. And there's many different components in place in a flare system to avoid that very situation. So you want to make sure that there's no oxygen coming into your flare header, there's positive flow always pushing out, and yeah, so the flare header essentially serves the purpose of taking your flare vent gas to the flare stack and to the flare tip. Okay, so now we'll get into the liquid knockout drum. These are usually the large drums just before the flare stack. Again, the main function for a liquid knockout drum is to knock out the liquids in your vent gas. So when your vent gas is going to the flare, it's going to have some liquids in it, and you want to make sure the flare tip itself is not designed to combust liquids, so you want to knock out those liquids before they get to the flare tip. And that's essentially what the purpose of the knockout drum is. It is important for a knockout drum to have the liquid level at the base of the knockout drum, and the reason for that is when the vent gas comes in at a high momentum carrying those liquid droplets, that momentum takes it into the knockout drum and makes it hit the liquid level down there. When it hits that liquid, it helps knock out some of those bigger droplets. When sizing a knockout drum, one of the important factors that comes into play is residence time. So if you can maximize your residence time, you can get rid of more liquid. So you'll see knockout drums that come in, and the more time it can spend in the knockout drum before it goes out, the better, that you can knock out more liquids that way. The other thing we've seen at times in a knockout drum is a mist eliminator right up there. And those are to get rid of some of your finer droplets of liquids. One of the disadvantages of a mist eliminator is that it can clog up, and then you'd have to replace it. So sometimes facilities choose not to go with that. But we have seen it. The other important consideration to make when looking at your knockout drum is if you're in a region with where your temperatures drop and you have the potential of the liquid freezing, you want to make sure that you have steam lines around the knockout drum to keep the liquid or the water in the liquid state essentially and prevent it from freezing up. Also, you want to ensure that you have enough capacity in your knockout drum when you're anticipating your maximum flows, because you never want that knockout drum to overfill or fill up. Usually there's a control valve at the bottom of the knockout drum that helps drain out those liquids, and you can send that to your slop header or and then replace it, because as I said originally, you should have a certain level of liquid in your knockout drum. So what happens when liquid is not knocked out of your flare gas? Well, not exactly, but this is an image of a liquid flare. So it is designed to burn liquids. As Herman said, one of his hobbies is driving around refineries at night. Another one of his hobbies is going on the internet and looking for cool GIFs of flares. So this is one that he recently found and kind of was looking for a place to put it in. So this is where he chose to put it in.
Yeah, I like that.
Okay, so continuing downstream, going from the knockout drum, we now reach the water seal, the liquid seal. Not all flares have a liquid seal, but so essentially the purpose of a liquid seal, it serves a dual function. One of them is to prevent flashback. So as I said earlier, you're going to hear me saying oxygen in your flare header system is no good. So similarly, oxygen in your flare stack, you don't want that to happen. But if it were to happen and you would have a flame in your flare stack, the liquid seal would provide a barrier from that flame, a barrier for that flame, preventing it from entering your flare header. So that's one of the functions of the liquid seal. The other function is it acts as a pressure barrier. So that liquid level that you have there, the height of the liquid essentially gives you a pressure barrier. And what you can do with that pressure barrier is, if you have an interconnected flare system, you can preferentially route your flare gas from one flare to another flare. Or if you have a flare gas recovery system or flare gas recovery compressors, that pressure barrier allows you to maximize the amount of vent gas you're recovering in the compressors. So usually we find that liquid seals are in a flare system that has flare gas recovery. But if you don't have flare gas recovery and you have the liquid seal, you're just constantly going to bubble through that liquid, or usually water, and send your gas up to the flare.
So when you do bubble through that liquid, the liquid usually goes into the weir right there, and then it can be drained out so that you can maintain that constant level. And you usually have monitors on your liquid seal that allow you to tell when you're at a high level or a low level, and accordingly the pumps pump water back in to maintain that pressure barrier. And again, here we show different configurations of liquid seals. You know, sometimes you can find them at the base of the flare stack down there, or you can find them upstream. We've also seen knockout pots and liquid seals at the base of a flare, so there's different designs that are possible. Yeah. So one of the things that, you know, yeah. What percentage of the flares have that? Yeah.
I mean, and really the whole steel thing, some we've found that it's so low that it's like barely an inch of water. Below that, it's purely there. So then, it's not as, I think as flare gas recovery becomes more and more prevalent, you'll see more and more. Both with the knockout drum and the liquid seal, if you're in a cold climate, you need to have to keep that liquid. If anything freezes up, you run the risk of not having a water seal if you're having a plug at that point. And you can have overpressure situations. Definitely something to keep in mind.
Yeah, so similar to the knockout drum, you know, you want to make sure that you have maybe a steam line if your temperatures go. Yeah. So, you know, some of the definitions that come into play when we talk about NSPSJA, when we get into it, are emergency flares or secondary flares. And in the way they're defined is that those flares must have a liquid seal or an equivalent device. So essentially a pressure barrier. So these are some of the equivalent devices, you know, to a water seal or alternatives. You have pressure control valves, buckling pins, rupture discs. And the main difference here is that, you know, once you break through a rupture disc, you then have to go in and manually replace that rupture disc. Whereas with a liquid seal, once you bubble through, you can have that process be automated based on your monitoring that you have on the liquid seal. But yeah, we have, you know, for certain facilities that do have emergency flares and don't have a liquid seal on it, and say they have a pressure relief valve or a rupture disc, we have put in alternative monitoring plans to the EPA. We've applied for them, and some of them have been approved also. So these are some of the alternative options to a liquid seal. And then we finally get to the flare stack. There's different kinds of flares. Again, as Herman showed from the ICR data, the most common type of flares are your elevated flares. You also have portable flares that you can bring on a temporary basis. And then you have the ground flares that usually are pressure assisted, and you know, we call them tulip fields, but we'll get into that too. All right, so moving up the flare stack, one of the cool devices that you can find on your way up the flare stack is a velocity seal or a buoyancy seal. And essentially, the function of the buoyancy seal or the velocity seal is, again, to prevent ambient air from infiltrating down into your flare stack. So for a velocity seal, you know, you're working off the principle that the air is going to come back down along the sides of the wall of the flare stack. So what the velocity seal does is it ensures that the purge gas or the vent gas coming through keeps that ambient air out of the flare stack, and there's always a constant upward flow. The other function that it serves is it also proves to be a purge reduction device. So you know, installing a velocity seal can end up in a lot of cost savings for your purge gas. And then with the buoyancy seal, how this works is If you have a purge gas that's coming into your flare and it's lighter than air, then it's going to accumulate up there, acting as a barrier for the ambient air to come back in. And if your purge gas is heavier than air, then it'll be down there in the bottom, and again, preventing ambient air or oxygen from going back into your flare stack. The Johnson. And the other concern that you know, one of the disadvantages of having these devices, and you know, one of the reasons that some facilities choose not to have it, is you could also have a liquid accumulation there or around there in the bottom, and if that liquid were to freeze, again, you have a situation where you're plugging up your flare. So some people have drainage lines from the bottoms to allow that liquid to drain out, which is what you should do if you choose to go with these devices. And then we get to the flare tip, which is you know, basically where the magic happens. The flare tip serves the function of mixing the flare gas and kind of creating that combustion zone, mixing the air and the flare gas, and creating that turbulence to ensure complete combustion and good combustion. You know, the flare tip is designed to operate in a dynamic fashion just because vent gas flow is so variable and so inconsistent that it needs to be able, the flare tip needs to be able to handle large flows and small flows. And this is actually a good picture of the flare tip. This is a steam-assisted tip, and you have your lowering steam lines coming in from the bottom. Through the center is also the center steam line, and we'll talk about what function that serves. Yeah, and when you're designing your flare tip, you know, it has to be able to handle the base load or emergency case. Other considerations to make are your metallurgy for the flare tip. You know, it gets hot up there since there's a flame and there's combustion. So it's important to consider the metallurgy of the flare tip, ensuring that you can maximize your flare tip life and you don't burn it off. So that's one of the functions of the assist gas, and we'll get to that too. So you have different types of flare tips. This here is a non-smokeless or an unassisted flare tip. You usually use this kind of a tip when you don't expect your flare to smoke too much. For example, if you have a high hydrogen flow or a high methane flow, something that burns pretty clean, you can use an unassisted tip without smoking. They usually have a smokeless capacity. That means, you know, beyond a certain level of vent gas, it's going to smoke if you don't have an assist gas. We also see these used as secondary flares, where you don't expect a high flow, and you know, you're only using it on your emergency case. But unfortunately, you know, if you do have that high vent gas flow to an unassisted tip, you do run the risk of smoking and having an exceedance. So assist gas, and Herman kind of touched upon this in the last module. You know, the main purpose of the assist gas is it actually has two functions. One is to help with the efficient functioning of your flare, ensuring good combustion, ensuring that there's mixing happening at the flare tip, and kind of creating a vortex to bring in that atmospheric air into the combustion zone to help with combustion. And the other function it serves is cooling of the flare tip, so extending the life of your tip. You know, whether you use steam or air, most tips come with a recommended minimum amount of steam, and that's usually considering how you can keep that flare tip lasting for a long time. So this is another cool picture of a flare tip. This is a steam-assisted flare tip, and here you can see the steam diffusers, and they're kind of pointed upwards at an angle, as you can see. So again, as I mentioned, that steam coming out at that angle helps create that vortex and bring in atmospheric oxygen. It helps facilitate combustion and complete combustion. You know, it helps for efficiently burning the vent gas. With steam, you can add it three different ways. You have the outer ring steam, and that steam is what would be coming out of these steam diffusers. Then you have the inner ring steam, which comes in at the base of the flare tip. and that's where you see those pipes coming in inside the tip. This one doesn't have it, but the drawing we saw previously had the lowering steam. And then the third way you can add steam is center steam, which is further down the bottom and right through the middle. The main function of the center steam is to ensure that the combustion is staying outside the flare tip. So it's kind of to lift that combustion zone outside the flare tip and prevent any flashback concerns.
A little story about this picture is that we were at a site and they were actually going to replace their tip. So that was actually a picture we have to take while we have to either flare off or they're interesting to see. Just take the time to look at them because you probably never get to see them ever again. They're going to go up
Yeah.
100 to 200 foot depth.
Especially with the air-assisted flares, those are really those have cool tips also. So, all right. And speaking of air-assisted flares, so air-assisted flares, basically what you're doing is you're replacing your steam with air, at facilities that maybe don't have the steam capacity needed for the flare. They use air, or if it's the temperatures fall drastically and you have the potential of the steam condensing, you can then use an air-assisted flare. The air for an air-assisted flare is usually provided by the blowers at the base of the flare. And the important thing to note here is that your vent gas comes in through this pipe and through the flare stack, and then your air is going in around the vent gas pipes, but they never actually come in contact until the flare tip. Any guesses for why that might be? Exactly. So, again, continuing with the theme of oxygen in the flare stack, oxygen in the flare header, not a good thing. So you keep those separate, and then combustion takes place at the tip.
What's the pressure of that air?
Well, that kind of depends on your blower settings. We've seen at facilities you have low settings or high settings. Preferentially, you would like to have a variable fan drive, which you can adjust based on the flow meter readings that you're getting. So if you have a high flow, you can then adjust your air to vent gas ratio. Yeah. And that is the aerial view of air-assisted flare. Usually you have the vent gas that comes in through those rectangular tabs, and then the air that comes in around that. And then we get to the pressure-assisted flare tip. These are pretty cool. We also, they're called the Coanda tips or the tulips, just because of the shape. And what happens in a pressure-assisted flare is you have your vent gas coming in through the stack at a high pressure, and because of the shape of the tip, it's forced to go around it. And when it does so at a high pressure, it kind of creates a suction around the bottom there that brings in the air into the combustion zone. So essentially, it's using the air from the outside to aid in combustion. If your pressure is not high enough, then you run the risk of smoking. As we went through 60.18 and it having the maximum exit velocity, with a pressure-assisted flare, you're usually going to exceed that maximum exit velocity. But the EPA knows that that doesn't necessarily affect combustion efficiency. However, you do have to apply for an alternative monitoring plan if you have a pressure-assisted flare. There are many of them accepted out there, and you can see them on the ADI, the Applicability Determination Index. However, it's not one of those cases where 1 amp applies for all. Every pressure-assisted flare needs to have that amp to operate at a high exit velocity.
One cool thing was that as of Friday the 13th, they published in the Federal Register where it was Exxon and Dow that requested they do some performance testing on some of these pressure-assisted flare tips, and they're asking for basically acceptability of those. Pretty cool thing.
Yeah. And pressure-assisted flares, they can be elevated, like that one's an elevated pressure-assisted flare, but they can also be ground flares where you have a bunch of them lined up with, we call them tulip fields, and those can be staged at different pressures so they can go off depending on how high the pressure in your flare header gets. Uh,
I don't know.
y-
One of those data points.
What other things performance would be really balanced?
Yeah, well, yeah, it's kind of like there's a stage approach, so it's kind of like they'll have that first line or a lot of times they also have a primary smaller flare for the normal releases, and then as the pressure builds in the line, then it goes over through the sewer and it will light off the different rows. But that's what, I think that's similar for the Exxon and the Dow group, that they have a primary control device for low pressure phase, but then it moves over to the sewer.
Right, and then, so we've discussed the flare tip. Moving on to the pilots. So the pilots are, you know, important for creating that flame in the combustion zone. You want to be able to always reliably ignite your flare gas, and that's essentially what the pilots do. You know, an alternative is you can direct your ignition of flare gas in the header or slipstream. So this is a pretty cool image of the pilots up close. And you want to, you know, you want to ensure that your pilot always has a constant flow of gas, and usually you'd like to have a gas going to your pilot that has a consistent BTU value, which is why most facilities choose to use purchased natural gas that burns clean, and you know, is usually what is used at the tip of a pilot. And then we get into the ignition system and what actually lights the pilot. So there are different types of ignition systems. The ones we most often see are your spark ignition at the pilot tip, or the high energy igniters. And they usually spark up when the thermocouples detect a high temperature. And then you also have the flame front generator, the compressed air flame front generator, which is at the base, which is at grade level. So what happens there is a combustible mixture is ignited down at the base, and that flame front travels from the bottom up to the flare stack, up to the pilot, and ignites the pilot. So those are the most common ones we see. We also have seen certain flare systems that have both, you know, one as a backup, so that's not uncommon either. And then moving on to the CCTV in your control room, you know, a lot of your control rooms have the cameras on the flare tip. You know, these are not so much, you know, they're not allowed, you're not allowed to use your CCTV camera for your method 9 and 22. However, it does allow the operators to have you know, have a way of viewing what's going on at the flare tip by being inside the control room. It's not vital to flare performance, but it is good to have that continuous monitoring, you know, and just keeping an eye on how things are going up at the tip. And then we move on to gas lines, the sweep and purge gas. Again, main function of the sweep and purge gas is to keep that oxygen out. So, you know, and to keep the pressure, to keep a positive pressure in the flare header, and ensure that there's always constant flow going to the flare stack instead of allowing any oxygen into the flare stack. We noticed that at facilities people interchange the use of sweep and purge gas, but there is a difference. Does anyone in the room know what the difference between sweep and purge gas is? So essentially the difference between sweep and purge gas is sweep gas is added upstream. If you have a liquid seal or a water seal, the sweep gas as defined by the rules is what's added upstream of the liquid seal, and your purge gas is added on top of your liquid seal, ensuring that you have positive flow through your stack. So it's really, the difference between the two terms is just about where that addition takes place. If you don't have a liquid seal, then your sweep gas serves the purpose of your purge gas. And you know, for the sweep gas and purge gas, you know, you could use natural gas or recovered fuel gas. Some people use steam, but the disadvantage with steam always is the potential for condensation. Yeah, again, we've spoken about the location and the function. So moving on to supplemental gas. You know, one of the important things that you need at your flare tip to ensure good combustion is a high BTU content, gases that have the ability to burn. And sometimes that might not always be the case, so you might need to supplement the gas going to your flare in order to ensure better combustion. And that's what the supplemental gas does. You usually take, say, natural gas typically and send it to the flare tip in order to add to the BTU content at the flare tip. And you can monitor, you can monitor that supplemental gas, or you can set a minimum amount of supplemental gas going up to the flare with an orifice. So that, basically takes us through all the components in a flare system. Next, we'll be talking about combustion calculations. And does anyone have any questions about the components? No? All right, so. Yeah, 10 to 10:30, so we'll see everyone back.
All right, I guess we'll get moving again, just to attempt to stay on time. We're going to enter into a slightly, I'm going to say less exciting module, but it's important, so bear with us, because I know as soon as I start showing equations, half the people in the room are just going to get on their phones and do whatever. So it's, I understand, but it'll help us with understanding. So we'll keep it brief. You won't actually have to calculate anything today. But we'll just talk about things. We'd like to start off this talk with kind of where the thought process goes for flares and the level of regulation there's been, and then the allegation. And basically that it's this concept of operating your flare with good air pollution control practice. So it says that even though there isn't a rule that tells you exactly how to operate your flare, you should know how, you should be operating in a way that is the best you can operate it. And then the other allegation is that it's common knowledge that how much steam or air you add to your flare impacts combustion efficiency. We've already shown today some of the studies from the 80s. They did more, they've been continuing to do studies. All the studies have been saying the same thing. Put too much assist gas, steam or air into your flare, you're going to have poor combustion. So that is where you may not have violated 60.18, but you still, the EPA still is going to say that you are in violation because you're not operating your flare correctly. So kind of wrap your head around that one. You didn't do anything against the rules specifically, but you didn't do what you were supposed to do. So.
How would they determine that? I mean, they would have to be there watching it. EPA would have to be there watching it in order to cite you by their determination. So is it the fact that somebody reported seeing smoke, or how do they report that?
No, it's from the over-steaming case, and now when they go to a facility and they'll do the 114 request, they'll ask you for a number of years, 5 to sometimes they'll ask for 10 years of data to say, what was the flow rate of gas going to your flare? How much steam were you putting on the flare? What was the composition of the gas going to the flare? What was the net heating value of the gas going to the flare? They will ask you for all that data. Maybe you have it, maybe you don't. If you don't have it, they ask you to estimate it. So, they're going to ask you for the data to basically go in and say. I think it is they're looking at sectors. I mean, they had, when we saw a lot of the 114s, early 114s coming out, they were going after the refiners. And then they were getting a lot of consent decrees from the refiners. And now it's kind of the progression that EPA seems to always take. Is they start with refining, then they'll move to chemicals, or to ethylene especially, and then they'll move into other chemicals. So I mean, it's kind of just how they're progressing through the system. So it's more that it's not that they know you specifically did anything wrong. They know maybe people like you did something wrong, and they're going to come and check to see what you're doing. So that's kind of where that, there isn't like some of your neighbor didn't call up and say, hey, I think they're operating their flare improperly. They're just going after the industry as a whole.
So when the neighbors complain about seeing flares in the sky or the aesthetics, I guess, of that, how does the EPA or the state regions generally handle that?
I mean, that's not, I mean, just because your neighbors don't like a flame doesn't mean you can operate your flare differently. It's, you still are under, even though people don't like it, you still are under an obligation to control those emissions. So I don't think they care that the public is upset about it. So yeah. So once they know that it's common knowledge, and then it's not good air pollution control, now is the fact that you should have known that you were doing something improperly. And they cite, here's some of the good studies. There's even more. There's the API guidance. That's another one they point to with the API 521 guide. This came, like, especially for refining, it's their body, their trade group's organization that's put out information to say how you should operate a flare. And if then you said you didn't operate your flare, then you're not even listening to your own trade group. So I mean, there's kind of, and the EPA is not stupid when they come to this thing. Is that they build the case against you? I mean, they're going to ask you, what did you know about flare operation? They're going to ask you, give me all the documents you have in your custody that you know or don't know about. They phrase it that way to tell you. That would have told you how to operate your flare. So then they ask you for the data to show me how did you operate your flare. And then they'll compare the two and say, well, look here, you have a document that tells you shouldn't have put too much steam to your flare, yet you were severely oversteaming your flare. So obviously you weren't operating it correctly. So I mean, that's kind of how the allegation travels. And so it's just because there isn't a rule that tells you don't put more than 3-to-1 steam on your flare, doesn't mean that you weren't supposed to stay under those ratios. So, and that is a hugely frustrating thing for industry. Everybody has a ton of regulation that we're having to comply with, and so everybody's very focused on that. And now it's coming out of, well, we didn't even tell you, through regulation how you should have done this, and we're still going to enforce on you. So I mean, there is some, people don't, they're kind of frustrated with that. So maybe through the new rules, hopefully there'll be some more understanding of what is requested of people. Okay, so we talked about flare performance, and so we have a couple of different concepts to kind of talk about flare performance. One is the no visible emissions, no smoking. We know that is regulatorily enforced. We want to have, and no visible emissions, you are allowed 5 minutes in any 2-hour period of smoking. That is allowed. Once you're over the 5 minutes, then it's an excess emission, or it's a reportable. Then there's those two words that I kept talking about, combustion efficiency and destruction removal efficiency. I'll show you the equations for those. And one thing you just got to understand is that with flares, direct measurement of a lot of things is not readily feasible at this point. So we're using, surrogate parameters, indicators of good combustion. And those are the things that get fed into these equations that then will help you understand how you're operating your flare. So, smoke. Got the 5 minutes in any 2-hour period. And smoke comes from a wide variety of things. The most basic is just that, everybody knows the classic stoichiometry to go from hydrocarbon plus oxygen goes to CO2 and water. Well, if you don't have enough oxygen, it's going to get short-circuited, and suddenly you're going to have unburned hydrocarbons. One of the things that happens a lot is, it's a hot environment. You're going to have some cracking of the molecules. And cracked molecules, what do they like to do? They like to reform up with other cracked molecules, forming larger particles that then form soot. So that's where you get a lot of your smoke formation. There's a couple of, we call these rules of thumb. The larger the molecules are that you're sending to the flare, the more likely they are to smoke. The more complicated the molecules are you're sending to the flare, the more likely they are to smoke. So it's that everything. Well, they tend to follow that general trend. So when we get into, once you're beyond smoke, which even smoke detection is a new science. We hear people talk about there is a detector that they say can detect the presence of smoke and adjust the steam rate for that smoke. We haven't seen that technology work at facilities yet. So if somebody can get it to work, that'd be awesome to see. We do know that there's a vendor here who has a new technique which they are saying that they will be able to monitor more effectively for smoke and control combustion. So go check them out at the next break. So we have a lot of these surrogate parameters that we're going to use to characterize good combustion. We got the exit velocity. We have the how much assist gas you're adding, and then it gets into the concept. Then we move from that concept into this net heating value based in the combustion zone. So talk about exit velocity, and this picture. If you get a consent decree, this picture will be in the appendix to the consent decree, because they will tell you how do you measure and determine exit velocity. I like this picture just because it shows you all three places where steam can be added. We are talking about, you have your ring steam here coming up the side. Here's your lower steam that comes in through the manifolds. And one thing that when it's not directly obvious is the steam manifold is down here in this area. This pipe is not connected directly to that steam manifold. There is a gap there. So that's where that oxygen is coming in with the steam. So there is actually the oxygen mixed steam coming up through those tubes. And then you have your center steam, which is just a little pipe that's providing the upward momentum. So we have the tip velocity requirements, the less than 60 feet per second, unless you know the heat content of your gases, then you're allowed to go up to 400 feet per second, depending on a calculation. One of the big issues of those tests that they use to determine those numbers is those were done on some of the smaller flare tips. So there's some discussion as to whether the test is really scalable. And I think if on Wednesday, I think Scott Evans from Clean Air Engineering is going to be doing some talks on the flare track, where he'll be discussing some of those parameters. So that might be a interesting discussion if anybody wants to go to it. One of the big things that we always like to point out is you think, okay, because you need the unobstructed cross-sectional area, because you measure the flow rate going up, the volumetric flow rate, you divide by the unobstructed cross-sectional area, and that's your exit velocity. But you got to just remember that depending on your tip, you have to remove the space of those lower steam tubes, and you also have to remove the area from the stability tabs that run around the ring of the tip. That's one thing that when you look at your tip and it says it's a 24-inch tip, that 24 inches does not include the stability tab. So you're going to have to adjust your calculations for that.
Are you just talking about the exit velocity of the flare gas,
Mm-hmm.
or flare gas with steam and oxygen?
It's for the vent gas. Yeah. It's not including the steam. The next exit velocity-based parameter is called momentum flux ratio. This came up through the enforcement track. We've seen in the marathon and the BP consent decrees, they have a requirement to control for MFR. That seems to be going away. We're very glad because most of the testing shows that this MFR issue is not an issue. So even in the proposed changes to max EC, which we'll talk about later, they don't want you to control for MFR. But what the concept is that it's a ratio of how fast the gas is coming out of the flare stack versus the crosswind velocity of the air. So they are always talking about you want to have a stable flame. You want to have an upright vertical flame, nice big luminous flame. If the wind is blowing too hard, it's going to blow over your flame. And if the flow rate coming up out of the flare is low enough, you're going to get these little turbulent eddies that are going to travel down the flare. And what they're really concerned about is discontinuous wake-dominated flow. You're going to hear that term used. And it's when you see a flame, and it looks like this picture, and this picture is also put in the consent decrees. And it's those little pockets where the flame is not continuous that they're concerned that you're not getting the combustion that you should be. This is a concept that is pretty contentious because the people, they're either on a for or against camp. And one of the things we like to point out is that this is a artist rendition of discontinuous wake-dominated flow because they couldn't get a picture of it. So and I think it's finally getting to the point where it's going away, but you may hear this term come up. So here are some pictures just to give you a better idea of what kind of things we're looking at. This was that wake-dominated flow where you see that licking down of the flame down the flare stack. This was a picture from one of those 2-inch flare tests. This is what you want to see, a nice upward buoyant flame. This is an older picture. In the newer consent decrees, they actually draw a little box right there to say that's the tip of the flare. And then this is what they call the inertia dominated thing, and it's difficult to see, but the flare tip is actually about here, and the flame has basically lifted off the tip. They want that flame to kind of be attached to the tip of the flare. So they're very concerned. They're even still talking about it in max EC about being concerned about liftoff because there's a high chance of basically snuffing the flame. So they're very concerned about this. So then we get to combustion efficiency. This was the metric we talked about already. This is complete combustion, going all the way from CO2 from hydrocarbon to CO2 and water. You generally like this. It's complete combustion. People understand it. That is contrasted with destruction removal efficiency. And this one, destruction removal efficiency, deals with specific constituents. So you don't care what the constituent turned into, you just care that it's not there anymore. So if you have some amount of 1,3-butadiene in your flare, you just care how much 1,3-butadiene made it through the combustion zone. You don't care if it cracked, reformed into some other hydrocarbon, you just care that it's not 1,3-butadiene. So I mean, that's kind of how the terms differ. Okay, so this is some pictures from the TCEQ study in 2010 and 11. They wanted to be able to, because one of the things when you want to measure destruction removal efficiency, you actually have to get samples of the constituents. How do you do that on flares? Well, they have this nice sampler here that they have a crane. And they hoisted this thing up into the air, and they went to those 2 test flares that they set up, and then they got in a downwind position, and they got it so this opening here was kind of in the direction of the plume, down downstream far enough that you're not in the combustion zone anymore. You have your nice positioning change because there were 2 guys out there that were charged with trying to move this thing to keep it in the right place during the test event. So, you know, it's in ambient conditions. There were no fans used. It's all wind moving all over the place, so it was not the easiest thing to do. They did use this was kind of the beginning stage of the PFTIR, the Passive Fourier Transform Infrared Spectroscopy testing, the open path technique that Clean Air and IMAC do. They basically were using those devices to see whether or not their devices matched up with this technique, to see if it would be an acceptable surrogate for it. And they were also used because they could see the emissions on their monitors and they could help point these guys in the right direction. So I mean, it was a pretty cool test. But who wants to performance test their flare like that? Remember the $2 million price tag. So we definitely don't want to be doing this, and we'd rather go to the passive techniques. One of the things in the TCEQ study were one of the things that you know, kind of gained some credence to the TCEQ flare test was before they even did the test, they sent out a survey to industry to ask them, how big is your flare? They didn't want to be able to be accused of saying, well, you didn't test on a relevant flare size. So they went out and asked everybody, what's your flare tip size? And then they picked a flare tip that was about the average of what people had out there. So you know, okay, this is a typical size flare. They also asked questions like, what is your normal operating condition? We want to know not what's going on at the emergency case. We want to know what's normally going there, because you know, just because you have an emergency that lasts 4 hours, that happens once a year, that's not as interesting as what's happening the rest of the time. So they found out that most flares are operating at a high rate of turn down. There's very little vent gas going to your flare at normal conditions. So they did these tests, and then they varied, like I said earlier, the heat content of the gases, and then they varied the assist rate to determine how that impacted the destruction and removal efficiency. Some of the caveats to the testing program is they said, well, we have to follow the regulations in that we have to have a flame present at all times. So they went to the snuff point. So that's where the data ends. Once they put the flare out, they said the test is over. And they couldn't smoke the flare. So that was kind of the bound on the test. Okay, so yeah, and then they verified with passive techniques. So when you look at that steam to vent gas ratio and you're looking at what's in it, this is a table out of API 521 that's telling you if you're sending various compounds to the flare, this is what API gives you for a range of values. API does not say where these numbers came from, and I don't know that they know where these numbers came from, because these are definitely not the rule of thumb for how people operate. Also, when you this table will be brought up in any enforcement action, as they'll say this is part of that evidence of you should have known where you should have been operating your flare. But it does illustrate a couple of points. Is one, as the molecules get larger and larger, the amount of steam required gets larger and larger. And as the molecules get more and more complex, you get more and more assist rate needed, again, to deal with the smoking issue. So here's 2 graphs. I don't want to get too caught up in the data, because we just basically took 2 random graphs because they all show basically the same trends. But so here's 2 cases they ran, and you can see here that they used 2 different BTU content gases and ran the tests. And they also, you did it at 2 different flow rates. So you can see at that beginning, you can have this area, which was shown in the earlier test done in the 80s, that when you have a low steam to vent gas ratio, you can get combustion efficiency up here around 98, 99%. Then you suddenly hit this point where you fall off the cliff. This was also seen when you increase the heat content of the gases, it just shifted the data down a little bit, which is kind of intuitive. You have more heat up there, you can put more steam up there before you're over steaming it. So, it basically showed that, the steam to vent gas ratio could get higher, but you still had this cliff effect. That's pounds per hour. It's this. They did two different flow rates. One thing, though, to know about this low case, this 350 BTU per scuff, and the low vent gas rate, in order to get that condition to show greater than 98% combustion efficiency, they had to decrease the steam going to the tip below the manufacturer's recommended minimum steam. So every tip has, on the tip drawing almost always, they'll have a number of minimum cooling steam that you need to put up to the flare tip to protect the metallurgy and to make sure it's ready for a relief case. So they figured out, though, that at this very low BTU case and low flow rate case, there was too much steam there as told by the flare tip manufacturer. And that kind of brings up a point, is that when you have your flare tip drawing, it'll have these various numbers. It'll have a minimum steam amount you got to put up there, and it'll have your minimum required purge gas rate. So how much purge gas you got to put in there to keep upward momentum. Those two are determined in two different ways, and they do not compare them back. So they don't say that, okay, with this minimum purge case and this minimum steam, you have a good combustible, or the chance for good combustion. They don't ever think about that. So at that base case, minimum purge, minimum steam, you could already be grossly oversteaming your flare. And we've done these calculations for a lot of flare tips, and yes, we're looking 50 to 1, 30 to 1, and that's what the tip manufacturer told you to do. We've seen people who are concerned about this. They've gone back to their flare tip manufacturers and asked, is this really the least amount of steam I can put to my flare? And there have been times where they've gotten from whoever it was, whether it's Zinc, Zico, Calidus, NAO, whoever, that sometimes that they will say, okay, yes, it is acceptable for you to take it down a little bit more to get you a lower minimum steam amount. So, Rashab talked about those buoyancy seals, those velocity seals, and how everybody loved them because they were what? Purge reduction devices. It saved you money. You didn't have to put as much purge gas up there. But that kind of exacerbates this issue of, at a very high turn down rate, you don't have enough combustibles in that mixture to keep good combustion. So that's something that is out there. It's known. Industry knows about it. The flare tip manufacturers know about it. EPA knows about it. But nobody's really addressing it yet. I think that we're all still trying to figure out how you can operate your flare at these low cases without having to maybe pump a bunch of extra gas to your flare. Because I think that the EPA is hesitant to tell you to burn a bunch of more gas in your flare. They're all about minimizing emissions. So it's how, they want to find another fix other than put a bunch more methane in your flare and cause a bunch more emissions. So it's still not exactly been addressed yet. Okay. But you can also still see here at some of these cases that where is this cliff? Well, here this cliff is somewhere around maybe 0.7. Over here, that cliff is, well, it's way back here, maybe around 1. So you still start thinking, okay, where did they come up with 3 to 1 is your maximum steam to vent gas ratio? It again has not really been shown in the data, but that's what they're still sticking with. So, you know, one thing that they found though, oh, that's one thing is, remember this is, they'll pull the steam to vent gas ratio back as much as they can until they smoke. And so where is the highest combustion efficiency? Right before you smoke. So that's what they found is they want you to operate your flare as close to that incipient smoke point as possible. So now if you go back to your facility and you want to, you say, you know what, we really need to get a handle on this or combustion issue. You go talk to the operators and you say, yeah, I want you to dial back your steam. And they'll say, but you told me not to smoke the flare. You said, yeah, but you need to turn back the steam. Well, I'm going to smoke the flare. They're very ingrained to know that smoking is bad, and you add more steam to get rid of smoking. So we've seen at some facilities that it does take a period of adjustment and education of operations staff to get them to get them to comfortably dial back that steam. Because if they don't feel comfortable with it, they're not going to do it. I like to also talk about this, you know, they show this picture and they say this was the incipient smoke point. And, you know, there's no good definition of a smoking flare. And so some people will say this is a smoking flare. Some people say this isn't a smoking flare. I'm going to leave that up for you to decide. I've heard certain people in the regulatory community say that this is a smoking flare. A lot of people from industry will say that's not a smoking flare. Of course, this is just a snapshot in time. So even, you know, when you're trying to control to this point or right to this point, you're at that kind of who's calling it smoking or not. For the air assist rate, they did the same thing for using the air-assisted blowers or flares. One thing they saw, it showed the same trend at that as you add more and more assist gas, you reduce the destruction efficiency. But what they didn't see was that shelf. They didn't see that kind of you're on that shelf and then you fall off it. They just showed basically a linear decline. But it's basically the same, the principle of a candle. How do you put out a candle? Well, you blow it out. So it's the same thing for an air-assisted flare. Yeah. So from that study, and even in the study, and if you ever have time, it's all available online. Well, if you like studies, it's a pretty good one to read. Lots of good data in there. They start talking about this concept of net heating value up in the combustion zone. They just bring it up, but then they say that was beyond the scope of our study, so we can't say anything about it because we didn't study it. So they kind of introduce the concept as saying this might be a good thing to think about, but the study itself doesn't comment on it. So now we're going to move into, so you basically need to be able to measure the heating value and the composition of your flare gases, because not all gases exhibit the same combustion profile, because we saw from the different steam to vent gas ratios that depending on your mixture, you're going to need to use a different steam rate. So I mean, and it's basically moving yourself up the flare stack. So this is the part, yep. No. JA is an NSPS, so it deals with criteria pollutants. Okay. So it's, yeah. It will be if the changes to the proposed max CC rule go through. So we're waiting to see if they get finalized. Yes, there is various for like flow monitoring, composition. There are, as any rule, there are exemptions. But for most of your flares, you're going to be into the ballpark of monitoring and control. But that's a CC issue because it's a MAC standard that addresses HAPs. So there you're caring about the destruction of the HAPs, where NSPSJA's cared about SO2, and you don't. The only way to prevent SO2 is yeah. No. Yeah, not yet, but it's consent decrees, yes. So it's yes, yes. So, and the equations that we're going to be showing you today, again, I'm not going to ask you to do any math, but these are the equations that come out of the consent decrees. So this is, this is where the kind of the math starts. And this is all, this progression is going to show you how do we calculate the net heating value up in the combustion zone. So the first thing you got to know is the net heating value of the vent gas. So you need to know what are the constituents in your vent gas. So that's where you're going to have your composition analyzer, whether it's a GC, mass spec, FTIR, there's a variety of techniques. But that's where you're getting this number. Then you're just using known published values of the net heating value for those constituents, getting the sum of the product to get your net heating value of the vent gas. In an enforcement case, the values for the net heating value, the EPA will provide those to you, and those do not match up with Perry's or some of the other literature. We don't know where they got theirs. They're close. They're all within like 5% of each other, but they're not the same, which will bring up some interesting things with your monitoring, because a lot of composition analyzers will give you your BTU content. They'll do this calculation for you, but are they using the right net heating values? So it kind of, that's another check you have to do beyond just buying equipment. Then you have to calculate the lower flammability limit of the vent gas. You want to make sure that that mixture you have up there is flammable. And so you're going to use this equation here. Again, you need to know what the composition is of the vent gas to determine that, because every one of those is going to be from a known value. One of the things, just kind of watch out, the EPA messed up in a few of the early consent decrees. They provide you with the units to use for each of these things. The units don't match up. So if you use the units they gave you, you'll be off by about a factor of 100. So watch your units, think about this, make sure the person doing the programming knows what units they should be using.
And you said the vent gas is including natural gas, or just the vent present?
Well, this is going to be like for your sweep gas. Your sweep gas would be measured by that same composition analyzer, so it will be in the vent gas. Anything put downstream of your analyzer will not be included in this number. Mm-hmm.
What I'm saying is, as a vendor, I get people to give me a list this long,
Mm-hmm.
of things they try and measure. First off, you take all those heavyweights, but the visible gases, come on, you don't have to measure them.
Yeah, we usually see them stop in C5 pluses is just gone.
I get a chemical balance engineer that lights up, here's everything coming out. You don't have to measure that. You don't have to measure it. Keep it simple.
Yep.
And make sure that they get that on. And then even up here, it's just that they have to be at least 300.
Mm-hmm.
So we're not doing chemicals, we're not doing custody transfer of natural gas. So we have to measure for 1 BTU out of 1,000.
Mm-hmm.
Factory field. You don't need that. Keep it simple. Again, the thing I'm shooting at is keep it simple. Going out in the field, this is not a money maker. Okay? Don't make it overly complex.
Yeah, and so that's one thing you got to understand. With the people that have done this to date, they have been under enforcement In enforcement, everything is negotiated. And so even the list of compounds that you are going to be measuring for and using in your calculations will be negotiated. So they'll start with a list. The EPA will start with a list of at least 20 components. If you can get some of those taken out, that's only to your benefit. But generally, yes, as you said, once you're getting above a C5, you're generally going to condense out and it's going to be in your knockout drum. So it won't be going there. And yes, and when we get into measurement, you'll be thinking about, do you measuring something down to a ppm level? Does that matter when you're doing a net heating value calculation? When something that's at 50 mole percent is going to drive everything, you don't really care what was 2 ppm in your vent gas. So there are techniques to, yes, simplify it down and do those things. Okay. This is the list that EPA gives you. So you can see it's about what you think. They've generally been capping at C5 plus. And this is something I haven't brought up yet. Enforcement and the rule writing sides of EPA are separate. They don't always do things the same. So you'll see where we have on enforcement that they pretty much all stop at C5 pluses. When we see some of the proposed changes to max CC, they go past C5 pluses. So it's kind of they aren't always in agreement, and we'll see a couple of other places in the instrumentation where you're provided different limits based on if it's coming from a rule or if it's coming through enforcement. One of the big things that people like to notice is the hydrogen issue. You get two numbers in enforcement, nowhere else. In enforcement, you can get two numbers for hydrogen. And basically, they figured out that hydrogen, well, like I said, you put it in a boiler, put it in a furnace, it's going to give you 274 about BTU per scuff. You can't physically alter that. But in a flare, hydrogen has some great properties. It's highly combustible. It wants to combust. It's going to help promote that combustion. So they said, well, how do we help account for that, that extra combustibility? And that was they allowed a other value for the net heating value of hydrogen to be used, and that was 1212. It is, I think it's out there publicly now, where you can actually see where that analysis goes through. But basically, they figured out that hydrogen's about four times more likely to combust than a hydrocarbon, so they gave you the higher net heating value. Being able to use that at higher value will kind of drive some of your monitoring techniques, because if you don't have a hydrogen number, you can't know how much to change it to. So it'll drive some of your decisions. Yeah. Yep.
So for that, net heating value of hydrogen, is there a guidance and typical stuff where they get the calculation and how they
Yes, I mean it's in the appendices of. I can get it for you. It's in an appendix of a submittal from, I want to say it was Flint Hills, but I'm not sure. But it was in there, and they submitted that to the EPA, so it's FOIA-able now. But EPA on the enforcement side has agreed to it because they allow it through the consent decrees. But rule writing, like for your 60.18 or numbers, no, that's not allowed. So it's only enforcement.
Are those heating values that the EPA uses, are those published?
In the consent decrees?
That's it?
Yeah. Yeah, no. I mean, yeah, we've taken these values and compared them to the various lists, and they're different from Perry's, and like we've taken some out of a couple of instrument manufacturers, and they're just slightly different. I mean, but like I said, it's 5 plus or minus 5%. Yeah. Yeah, so it's all kind of, they're close. So it's just something that if you're in enforcement and they've told you what to use, you have to use it. So if you're not in enforcement, then you can use the values you're most comfortable with. So, yeah.
I got a customer with a flare. I don't think he has an extended free on it. He's using a DC belt and all those parameters. I don't know.
Mm-hmm.
It's all.
Yeah. So a lot of times we'll say, like with the calculations, is don't do those calculations inside of the instrument. Bring the composition data outside of the instrument and put it into either a DOS or your DCS or something, and have that calculation done out exterior to the device.
You recommend that from a regulatory perspective or an operational?
I recommend it just from so you know what's going on in your compliance. If someone were to say to you, show me that you're using the right numbers, instead of trying to go into the device to figure out what values it's using, you have it all external. Yes. Yeah. And when you get to the data side of this, is you're going to be taking all the data you can get and taking it and post-processing a lot of it. So I mean, it's better to have the data because you can use it all in all these different ways than to have it not have the data. So when you think about lower flammability limits, we have this concept of the nose plots. Won't spend too much time, but here you can say it's just basically saying if you have a mixture of a combustible gas in with, like, say, nitrogen, and you're going to have a composition range where that mixture is flammable. You're going to have below that, it's 2 nitrogen, or no, it's in oxygen, sorry. So it's going to be too rich or too lean. And so basically you want to be in this window. So as you're coming in, you want to be in this zone where you're going to have an actual flame be present, have the gas mixture be flammable. If your mixture is not flammable, it's pretty hard to have a flame. Where this gets, and so where when you think about it coming out of a flare stack, is you're coming down this path here, and that corresponds to coming up out of the flare stack here. So when you're first coming out of the flare tip, again, remember we tried to keep oxygen out everywhere. So there should be very low oxygen. But you're going to be very fuel rich, and that's where the mixing comes in. So as you're getting mixed with the atmospheric oxygen, you're going to then hit this upper flammability limit. That's where you're going to have the combustion start. Then you're going to, as the fuel is expanded, as it gets more mixture in with the ambient oxygen, you're then going to finally get to the point where you're lower flammability limit. So then you're not going to have a visible flame. They use this phrase here that says post-combustion. I don't like that word because there's probably plenty of heat and energy still in that gases, so it's still going to be reacting and oxidizing away, so it's not necessarily post-combustion, it's post-flame zone. So just, I just don't like that word. But so just kind of to visualize that zone, and that's where you want to have that good combustion in that zone. But then you start getting into, well, it's easy enough to do that analysis when you have a single mixture, but when you start having a lot of different components together, these combustible zones kind of get a little confusing. So I mean, that's where that equation was with the inverse of the lower flammability limits, that you're using that combustion or that calculation to determine the flammability of your mixture, which again is read from your composition analyzer, which is being collected as the flow varies and the composition varies. So now we need to go up to the tip. And so this is where you take that net heating value of the vent gas you multiply by the the lower flammability limit of the vent gas, and then you have to, you're trying to calculate your limit. What is your benchmark where you need to be above to have a combustible mixture? So then there's a couple combustion variables that they provide you. You have to take into account the concentration of propylene, and that will give you what's your limit, what you need to be above to show good combustion. Let's see here. Those combustion efficiency multipliers are shown here. You know, kind of depending on where your minimum steam is, I'll put you into one of the two cases. Then you're looking at the VOC concentration. Remember, methane, it's not a VOC. So you got to take that and remember that when you're doing these, picking these multipliers. So then you get that, and you know, this B multiplier depends on your hydrogen concentration and your propylene concentration. The propylene, everybody says, well, why do we care so much about propylene? There was some testing done, and they basically showed that when you're combusting mixtures that are high in propylene and hydrogen, you have this where it falls off quicker than other mixtures. And so they have, and then they came up with a hypothesis, because there hasn't been a lot of study in this area, so it's still kind of people guessing at what's happening. But basically they're saying that when you combust hydrogen in the presence of propylene, it forms some stable intermediate products in combustion. So they become stable, so then they don't continue down the combustion path. So it kind of short circuits the combustion early, and so you can have where you're going to drop your combustion efficiency quicker. Again, if you see Scott Evans from Clean Air, I'm pretty sure in his presentation on Wednesday, he's going to have a lot to say, because this propylene issue has come up again in MACCC. There's a hydrogen olefins interaction that will force you into different control parameters. He has a lot of interesting things to say on this point. But so even the test data and the data they use when doing the analysis is somewhat in question. Okay, so we figured out where we had to, what was our limit. Now we need to figure out where we're at. So that's your net heating value in the combustion zone. And here's where you're taking into account basically the heat coming from your vent gas, the heat coming from your pilot gas, divided by the pilot gas. And this is where your assist comes in. And so unless you have a dual assist flare, you will have, this is, if you only have a steam assist flare, this term goes away. This is not like the atmospheric oxygen that you need to come. If you have just a purely air-assisted flare, then the steam number would be 0. So that kind of shows you. But if you have a dual assist flare, you would need to have both of these terms in the denominator. So you can see, if you add more and more steam or more air, you're going to make it harder and harder to meet that combustion zone parameter. And so from the consent decrees, and especially this is the earlier consent decrees, I think they've started to move away from this, which is a good thing. What you had to show was you're higher than your combustion zone limit, and you still have to be higher than 300 BTU per scuff in the vent gas. You never get rid of your subpart A requirement. That's always going to be with you. But one of the things to think about, though, is this CZ limit was calculated based on the concentration from your analysis, which is going to happen depending on your technology. It could be every 60 to 60 seconds to 10 minutes to 15 minutes. So now you have a moving target of where you need to be. So not only are you trying to control all these parameters, now where you're trying to control to is going to change every time you get a new output from your analyzer. So just to make things nice and confusing. They've started to move to where instead of a CZ limit, they've started to move to where there is a fixed number that you're going to have to control to. So that will make things a whole lot simpler once everybody gets around those numbers. And there are numbers in the proposed max CC rule that are there that will show you towards the end of the day. Okay, so I just want to illustrate a couple of examples, just to kind of, we basically made up these things to just kind of show, you got your flow rates, a minimum steam from your steam, the tip manufacturer. You have a steam to vent gas ratio of about 0.5. You get your multipliers. You go through your calculations. You get your net heating value, your vent gas, 900. You're doing great. You calculate your lower LFL. Calculate your the LFL of the vent gas. Get your combustion multipliers. Again, because methane and ethane, not VOCs. So you get a net heating value combustion limit of 225, which you can see is lower than the 300. So I mean that's a different limit. And so then taking your flow rates and just no air, you're going to get, using the flow rate of your pilot gas, you get a net, with a CZ limit 225, you have net heating value in the combustion zone at 591. So you're good. You're above your net heating value of your vent gas. You're above your combustion zone limit. Now we had, a pretty good flow rate, not a high steam to vent gas ratio. Remember, it was 0.5 to 1. So then we look at case 2, which is typical of a lot of flares. We talked about flares that have flare gas recovery. You're only going to have that minimum purge case. So we're going to look at that minimum purge flow rate, which can be very low numbers. I mean, that was the whole goal, was get that amount of gas you need to put up your flare as low as possible, save you some dollars on purge gas. Got your other combustion, keeping the minimum steam the same. Go through, still good in the vent gas, 896. Got your LFL. Combustion zone limit, 289. But here you start looking at it, net heating value in combustion zone is 52, where your limit was 289. And when you look at your steam to vent gas ratio, 24 to 1. So I mean, these are numbers that you will see coming from your tip drawings. So I mean, if you're looking at that base case, purge only, minimum steam, you could be over-assisting quite a bit. So, how do you correct for that? Well, you got to add supplemental fuel, because you need to do something. And the only thing you can't really take out steam. You can't take out steam below your minimum steam requirement, or you can't take out the steam that you're using to control for smoking. So the steam control is kind of slightly separate. So how do you work on this is you got to do add supplemental fuel. So wait a second. Okay, so here's when you're looking at the cases before, if you wanted to add supplemental fuel to that last case to get yourself back into control, into good steam to vent gas ratio less than 3, you were having to add an additional 4,000 scuff per hour of natural gas. If you wanted to be in compliance with your CZ limit, you were going up to 4,400 scuff per hour of natural gas. Once you've added that much natural gas, that drove your steam to vent gas ratio down to about 2.4. So it kind of illustrates that you didn't have enough gas going to your combustion zone to have good combustion, and it played out through the 2 different parameters. But that's a lot of extra gas. I mean, that's almost like, it's almost like, why did you have a molecular seal or a velocity seal in your flare at all? Because it didn't, you're going to have to put that gas back in there if you want to show compliance at all times. Air assist. These calculations are totally different than steam-assisted flares. You see, you know, basic chemistry. Everybody generally knows these equations because when the EPA, they came out with a paper called the Parameters for Properly Assisted Flares. In that, they talked about this concept of stoichiometric ratio, and it's determining how do you have enough oxygen in the combustion zone to have complete combustion. So basically, won't spend a lot of time on the calculations, but basically, the more carbons you have, the more oxygen you need. Pretty straightforward. So then you're calculating, you had your moles of oxygen, now you're getting you have to convert to the mass of oxygen you need. And then you got to go from oxygen to air, because nobody's supplying pure oxygen to their flare. At least I hope not. That's an expensive way to do it. So then you're getting your mass flow rate of air that you need. And then you're just making sure that the amount of air you're supplying as your assist is some factor x, is less than some factor x times the stoichiometric amount of air that you need. What is the x factor? This is, there's lots of different numbers out there. The OAQ, the parameters paper from OAQPS, they fixed on 7, but then they go and have a consent decree with BP Whiting. They have an air-assisted flare. They got a parameter of 10. We've seen numbers of 6, seen numbers of 5. There's not, I think this kind of is the point where EPA, I think, understands steam-assisted flares. They've had a bunch of performance tests done on steam-assisted flares, and they're not asking for them anymore. It seems like they've said, okay, we understand them. The EPA's focus has shifted to air-assisted flares. And so they're really going after people who have air-assisted flares. So if you have one and you're in an enforcement situation, don't be surprised if they come to you and say, we'd like you to perform some performance testing on your flare because we want to because basically they want to understand these concepts more. So I mean, it's kind of through enforcement, getting you to do some nice little studies for them to let them enforce on a whole bunch of more people. So it's not as well known. And when we get to Max CC, they throw in another wrench. But I'll wait till later to put that out there. So just to summarize, you need to know the composition. For this technique that's in the consent decrees, you need to know the composition. This is where everybody likes to talk about BTU analyzers, calorimeters. This is where EPA doesn't like to go down that route. So you're finding out that you're calculating the various net heating values, the LFLs, and then determining your limits to make sure that you're above both the combustion zone limit and the vent gas limit. The air-assisted flares, similar. Need to know what's in you have to know what's in your composition, because how else would you know how much oxygen to put in? It's compound specific. So you're going to need to know those compositions, calculating how much air you need, and then having a ratio above that in which you need to stay below. So everybody wants to know, everybody wants one thing to look at and to know they're performing well, that they're doing what they need to do to have good combustion. So, you know, we've had through the years, we've had different parameters. You know, we've talked about the exit velocity, how much assist gas, how much net heating value. And basically, there is no one parameter. And, you know, even though it looks like net heating value looks like the strong contender right now, doesn't mean they're giving up on exit velocity. They're still making you, requiring you to comply with exit velocity. And they're still talking about your steam to vent gas ratios or how much air assist you're putting in. So I mean, it's more that we're not throwing away anything, we're just adding to it. So it's just making the calculations more and more complicated, the monitoring more and more robust. Okay, questions? I know that's probably the worst one, I'll tell you. Okay. I just like people to know that that was the worst one. And I cannot find my mouse. Where is the mouse? Does my finger not work? Oh. Come in. Which one is it?
Okay, so we spoke about calculations, and after lunch we're going to talk about control. But in order to calculate all the things you need to calculate, in order to use your control systems, you need to have that data, such as your vent gas flow data, your composition data, and so that's what we're going to talk about. Your monitoring options when it comes to your flare system. So the main components when it comes to monitoring is you have flow monitoring for your vent gas, steam, air, supplemental fuel. And some of the major players when it comes to those flow monitors for flares are GE, SICK, Fluenta, and OSI. Those are some of the main vendors we've seen in the industry. We look at flares in terms of compliance at Sage, but we also try and get into the technologies out there and the different vendors. Every instrument has its advantages and disadvantages, so that's some of the things we'll be discussing as part of this module. Then you get into your composition monitoring. NSPS-JA has a huge focus on sulfur content monitoring, H2S monitoring. And then with your consent decrees and potentially MAC-CC getting finalized later this year, you'll have the net heating value requirements, and for that you could use BTU analyzers as well. And then we'll talk about a few other monitoring aspects on your flare system. Again, some of the vendors that we've seen out there, you have Thermo Scientific with the Solar 2, and the Solar 2 is used for your total sulfur measurement as required by NSPS-JA. Yokogawa, Siemens, Rosemount, they make GCs. And then you have the Yokogawa, Servomex, Amatec TDLs, and we'll get into that. And you also have IMAC, which uses FTIR and Raman spectroscopy to get your constituents in the vent gas. Okay, so let's start with flow and on your vent gas. What we have up here is your typical GE flow meter. It's the GF868 model, and this is usually what we see at refineries. About, I would say, 90–95% of the time, it's usually a GE flow meter. And the principle it works on is ultrasonic measurement. So it uses ultrasound to measure the vibrations and the disturbance within the flare gas header and measure the flow rate of the vent gas going through. So you have your transducers that measure that disturbance, and then you also have pressure and temperature correctors. They are retractable, and you can maintain them while the flare header is still in operation. So this is so one of the reasons the ultrasonics are so popular when it comes to flares is because as your header gets larger, it's harder to measure that flow, and so ultrasonic has proven to be a pretty reliable technology when it comes to larger piping and larger flare headers. And really, the issues that you face with the larger flare headers is the low flow condition. You know, it's harder for these transducers to be able to pick up that flow at low flow conditions. So GE actually recently came out with a new transducer called the T17 transducer. So you'll hear T5 and T17 pretty often. T5s are usually what you find at refineries right now. And they're pretty good at high flow conditions, but at the low flow conditions, the signal is not strong enough to pick up the low flow. And so GE came out with the T17 transducer. And essentially what it is it's 4 T5 transducer heads put into one. And so that signal strength gets stronger. You know, and as people are experiencing issues with their flow meters, GE has been recommending switching to the T17s. However, the limitation there is that the tap that you need for your T17 transducer has to be 3 inches or larger. So it can't be smaller than 3 inches, whereas the T5 can fit in a 2-inch tap. So if you have a 2-inch tap with your T5 transducer, you probably won't be able to replace it without making a modification to your header. So now we'll get into some of the configurations that we find with these flow meters and the transducers. The first configuration is the bias 90. And basically what's happening here is you have the 2 transducers and they're both pointed towards each other so that that signal is being read by each transducer and it's measuring the disturbance between it. You can have it installed on the side like that, so these 2 would be a pair and those 2 would be a pair, or you could do it vertically, where those 2 are sending a signal across. So this kind of shows you the path length between the 2 transducers, and the longer the path length that you have, the more accurate your measurement's going to be. So that's kind of why you'll see, you won't find the 2 T5 transducers lined up like that, because that would mean the path length would be too small. So kind of to maximize that path length, you have them kind of offset from each other. Another very common configuration is the diagonal 45 or 180. And they come into the side of your flare header at an angle of about 45 degrees. And what this does is it maximizes your path length. And this is a good configuration for your low flow conditions, whereas the bias 90 is better at high flow conditions. And of course, with the T5 transducers, if your header is too big, the signal, it won't be able to read. The 2 transducers won't be able to pick up the signal from each other, which is where your T17s come into play, and that's where this is the ideal configuration. With the diagonal 45, it doesn't have to be diametrical in the middle. It can be mid-radius too, so that this just illustrates that. And then we get into the single versus dual channel flow meters. You can have 2 sets of transducers, maybe one downstream of the other, and if everything's going fine and you're getting good readings from both sets, then that's great. You can average out those readings. You can use them as a redundant pair of transducers, so that way you're minimizing downtime in case you have to perform maintenance on any one of them. Does it add accuracy? That's the question. So we have seen a facility that had a set of transducers on their header and then another set downstream, but the 2 sets were off by an order of magnitude. So, I guess it's kind of, we can't really definitely say that it adds accuracy, but it can be, if everything's going well, it can be used to average out your readings and prevent monitor downtime. The dual path. So what we saw so far with the two transducers or one set of transducers is the single path. Now we have 2 sets of transducers, so a total of 4, and that's what we call the dual path. This configuration here shows, so with the T17 transducers, you cannot install them in the bias 90 configuration because of that transducer head that has the 4 T5s. They're too big for them to be installed as a bias 90, and you can't point them towards each other. So if you have a T17, it has to be diagonally across like that. So we've seen T5s at the bias 90 and T17s across, Or what the ideal configuration is having 4 T17 transducers with that crisscross configuration. So it's kind of a case of good, better, best. So this would be better, that would be best, and your good is your T5 bias 90s. So, you know, every technology has its issues, and in the case of the ultrasonic flow meters, the issues are reading nitrogen and hydrogen, the diatomics. You know, so the GE flow meters and basically most ultrasonic flow meters have a problem reading the nitrogen and hydrogen gas that go through your flare header. GE has provided a correction factor for nitrogen, and that has to be used along with your GC or any other composition analyzer in order to correct for that nitrogen. With the hydrogen, you know, basically with the ultrasound, the density of the gas going through your flare header matters, and since the density of the hydrogen is so low, it's harder to get that signal to detect it. And that's why GE came out with the T17s also, is because it provides better accuracy with hydrogen. So this table is, you know, the different models of flow meters that we've seen out there. You have the SICK flow meter. This is the OSI optical flow meter, and they have a booth out in the exhibition area, so you can check them out there. And then you have the GE ultrasonic flow meters as well. What we want to point out from this table primarily is the required downstream distance and the required upstream distance as recommended by the manufacturer. And this can sometimes be an issue if you don't have a long flare header. The ultrasonics, as you can see, need about 10 pipe diameters or 20 pipe diameters downstream, 10 downstream and 20 upstream. And you know, with the SICK and Fluenta, with the Fluenta, it goes down to about 5 and 10, but the SICK still has the 10 and 20. So in those cases, if you don't have enough of a straight run pipe without a bend or a disturbance, that can affect your flow readings. This is recommended by the manufacturer, so you know, that's when if you had problems with your ultrasonic and you didn't have that straight run of pipe, you would then get into issues of whether you maybe install a trombone piece to give yourself that extra pipe, or perform, you know, have GE come and perform some fluid dynamic studies to see if your flow meters are working correctly. Now, what's important to notice here is that the optical flow meter has a very low requirement of 1 pipe diameter downstream and 2 pipe diameters upstream. The downside of the optical flow meters is that it only gives you velocity, so it won't give you mass flow rate, which you know, is okay for JA and certain other requirements, but with MAC-CC, it would become a problem. You'd have to use it with a composition analyzer in order to determine your mass flow rate. Okay, so now we'll get into flow meter accuracy, and you know, a lot of those flow meters, as you can see, the flow range goes pretty low, but most of them stop at around 0.1. You know, the manufacturers say we can go down to 0.1, but any lower than that could be a problem. And NSPS-JA and MAC-CC actually do not allow for a very high inaccuracy percentage. The 20% is usually what you see in consent decrees, but JA and MAC-CC only allow about 5% inaccuracy, and that can sometimes be a problem. So that's what we're trying to illustrate through this table. Is we looked at flow rates going up from 200 to 1600, and then we looked at the different sizes of your flare headers. And as you can, and these numbers here are the velocity in feet per second of your vent gas. So as you can see, even at low flow rates, you get out of that 0.1 range very soon. You know, in a 1.5 feet header, you're out of it at 200 CFM. And as your header gets bigger, even at a high flow rate like 600 cubic feet per minute, per the manufacturer, that flow meter is probably not going to pick up your flow. That's based on the 5% inaccuracy allowance that JA and MAC-CC allow you. But if you were to take the 20% allowance that the consent decrees allow you to have, then that gives you a much higher range of acceptance. So you're still within that 0.1, but for a 2-foot header, you can go as low as 200 CFM, and it can still be detected by your flow meter. So that allowance becomes important, and I think, Herman, correct me if I'm right, I don't know what's happening in MaxCC, but are they trying to get that in there, or? Right, so that's the main concern. And okay, we'll move on from vent gas now onto steam flow monitoring. So with your steam flow monitoring, you don't have any requirements as such. The only requirements for accuracy that we've seen have been in the consent decrees. It doesn't require you to use any type of flow meter or any type of technology. As long as you can meet those accuracy requirements, you should be good. With the steam flow meters, of course, they tend to get very hot. So we do recommend that if you're going to install a steam flow meter on your steam line, that you have a bypass valve around your flow meter so that if at all you need to pull that out for maintenance, you can use the bypass to provide that minimum amount of steam as recommended by your flare tip manufacturer, and then allow the steam flow meter to cool down, and it'll take some time to cool down, but having that bypass valve becomes important to allow it to do that. Okay, moving into the supplemental fuel gas and purge and your pilot gas. With the supplemental fuel gas, again, there's no technology or accuracy requirements that we've seen in the consent decrees. So you can usually control that with a restriction orifice. Just like your purge and sweep gas, you can use a restriction orifice or a back pressure regulator. If you have a set flow rate that you want, again, the flare tip manufacturers recommend a certain amount of purge gas to be sent. So you can set that using that regulator or orifice. Pilot gases are usually set at a constant rate to ensure the presence of the pilot. So, again, a restriction orifice works pretty well for that. Okay, so that was flow, and now we'll move into flare gas composition monitoring. Okay, so the main technologies that we have seen and we have encountered so far have been your GCs, gas chromatography, and it's a good technology. It's widely used in industry, so we know it works. And the early CDs actually specified using GCs. The only downside with GCs is the sample time. A quick sample can take about 7 to 8 minutes, and a slow one could go up to 10 to 15 minutes. So you're not kind of getting that instantaneous measurement of what's going to your flare. And then that becomes an issue if you're trying to control your BTU contents at the flare tip or your steam to vent gas ratio. So that sampling time becomes a problem. With your Fourier transform infrared spectroscopy, again, it works great at detecting the constituents going to the flare, but the downside is it doesn't measure diatomics. So your nitrogen, hydrogen won't get measured by FTIR. Mass spec, again, great technology to speciate. The downside for mass spec is you have a bunch of cal gases. So, you need many different calibration gas cylinders on site, which can then become expensive and inconvenient. So maybe a combined approach would work, such as FTIR and Raman spectroscopy. So where FTIR lacks is the ability to detect your diatomic gases, whereas if you include Raman spectroscopy in the monitor, then that can compensate for the diatomics. So the combination of the two, which we see the vendor IMAC has an instrument like that that does that, can work pretty well. Then we get into the BTU analysis and the net heating value measurement. For a BTU analyzer, the main principle that it works on is, it takes your vent gas and it combusts it using a certain amount of oxygen. It sends a certain amount of oxygen and combusts your vent gas, and then it measures for the residual amount of oxygen that it then uses to correlate with the WOB index, and that kind of gives you the net heating value of your vent gas. NSPSJ has a H2S requirement of 162 ppm on a 3-hour rolling average. So some of the monitors that, some of these monitors are specifically made for JA compliance. For example, your tunable diode laser, it's a laser that is tuned to detect a gas at a certain frequency. So in this case, it would be H2S. So all it can measure is H2S, but it does a good job at doing that. Yeah. Staying on the JA track, you have the total reduced sulfur requirement. JA says you cannot emit, or you would trigger RCA at 500 pounds of sulfur dioxide, and it allows you to measure your total reduced sulfur to meet that requirement. And that's where Thermo Scientific has a device called the Solar 2 to measure total sulfur. They actually have a stall here also at 4C, so you guys can go check that out also. On these devices, you have to perform your daily calibrations, your CGA and RADA. Again, you use your cal gases for that. And then we get to some of the other monitoring points on the flare system. On your liquid seal, you check your water level. Pilot presence, you have the thermocouples that detect the temperature at the pilot. And you can use IR or acoustic sensors for that as well. Pressure sensors become important if you have a flare gas recovery unit. How do you stage your compressors? Do you have multiple recovery compressors? It's important to measure that, measure that pressure so that you can create your set points to recover that flare gas. And then you can have acoustic monitoring on your high H2S valves. In case you have certain PSVs on a process that has a high H2S, in order to make sure you're not leaking high H2S gas to your flare, which would then push you over that 162 limit, you can use acoustic monitors to make sure that they're seated properly, or every time they lift, they come back and, they're not leaking anymore. So that was a quick, rundown through all the monitoring options that you have when it comes to flares. And we can always get into further detail, but as we try to keep moving along, I think it's about lunchtime now. So next we'll be doing control strategies back at 1 o'clock.